Morning.
Hey, Miguel.
Yeah.
What's about that? We're going for it. But we have to send it. How do we send? What is the email again?
I can just move it over there. It's on. I don't know.
Oh, you can just put it in the. No, I can just put it in the
I'll
doc.
just try to get this.
We have 1 minute. How do I?
Great.
Should we give it another minute? Just go ahead. Oh, we should probably go. Great. Okay. Why don't we go ahead and get started with, well, I'll just project for two. With day 2 of FRB 2025. We'll give a little bit of a longer introduction today because hopefully a few more folks have arrived into the conference and some of the people we want to thank. We'll go ahead with a little bit more of an introduction of ourselves. So I'm Alice Curtin. I'm in the last 2 weeks of my PhD, actually. And then in the fall, I'll be starting as one of the first Canadian SKA scientists. I'm really excited.
And then my name's Amanda Cook. I am a Banting postdoctoral fellow at McGill University. That's it. So we want to again thank the people who funded this conference. So we had support from the Astroflash group as well as the Canadian Excellence Research Chairs. We had some funding from Trete Space Institute, and then McGill helped us with a lot of logistical stuff and didn't charge us that much for the room, etc. So thank you so much to them. We also wanted to take a second to talk about the scientific vision of this conference and in particular who made it possible. So could we have the SOC members stand up? So these are, and we just kind of wanted to give a special highlight for this group. These are the early career SOC members, and I don't know, we had a couple ideas going in, but I have to say that this SOC really helped us just mesh the vision together. And I'm going to talk about some of the scientific themes we came up with. One of our big goals for this conference was to, of course, capture the latest in FRB, make sure a broad range of people are talking about what a broad range of people are interested in. And so here are kind of the scientific themes from this point going forward. So today we're going to talk about populations. We're going to talk about repeating FRBs. We're going to talk about what we're going to do as we detect thousands and thousands of fast radio bursts, in particular, how we are going to learn about their host galaxies and gather information. We're going to talk about some single sources. Tomorrow, we're more focused on galactic analogs, so ultra-long period transients, magnetars. What is the role of these galactic analogs in our field? We're also going to talk about FRB polarization. It's been a huge year for FRB polarization, and we'll hear some more of the observational discoveries around that. Day 4 is about emission mechanisms. So not only just theoretical emission mechanism research, but also the observational signatures of different emission mechanisms and how we can use observations to disentangle information about the emission mechanism, as well as FRBs as probes. So the circumgalactic medium, cosmology in general. And then finally, the last day is focused on the next generation. So what are the new instruments? What are the new surveys? How are we get there? What are we learning along the way? There's a really special tie. So we have a very special anniversary this year, and it's the 10th anniversary of the first repeating FRB. So we have 4 guests to speak about this big anniversary. So we have Laura Spittler, Paul Schultz, Shami Chatterjee, and Jason Hessels, who are all going to talk about that day that we learned that FRBs do occasionally repeat, at least. And it's kind of a special tie for McGill too, because at least some of the data analysis was done right here, which is fun for us to look back on.
So we had one goal, which was to kind of broadcast all the fantastic science, but we had another really large goal, which was to make this conference very equitable and accessible to all. And that has really been kind of done in large part thanks to our LOC. So I'd like our LOC members to stand up. And I would really like to highlight that everyone you see is an early career researcher, and they're also the ones, they're making your coffee every single day. They went out and bought all the snacks for the conference. Really, everything has been kind of handmade, which is what allowed us to make this conference at a fairly reduced rate for most folks. And we were able to give fee waivers to every single person who requested it. And it's really on behalf of these people who are going out and doing things for you and giving up some of their conference time. So I really just want to emphasize their efforts.
So kind of just some fun facts in case you're curious about McGill or this conference in general. We have about 110 people in person here. And then there's 100 people additionally participating online. We're in the chemistry building at McGill, which is the auto mass building. McGill in general has about 40,000 students at any given time. and it was established in 1821, and it's one of 4 major universities in Montreal. Kind of one of our claims to fame and something we're really proud of is that Ernest Rutherford had taken, so he showed that elements could disintegrate and be transformed into other elements, so just radiation, and he did that just across the path here. So I have this little map of where we are. You can see the old physics building. And he won a Nobel Prize for this work, of course. And so part of the program of this conference will also be you can go and see some of this apparatus between the end of the conference on Wednesday and before the conference dinner. Also in that time, we'll have some guided tours. So we'll have lab tours of Matt Dobbs's radio and millimeter labs. You can go visit them in that time. And we'll also have an open house of the Trottier Space Institute. So if you just want to see where we work, if you want to see where the R1 data analysis was done, we'll show you that office before leading you up to Thompson House for our like cocktail style dinner at 6:30 on Wednesday.
So a few kind of reminders from yesterday and for folks who weren't here yesterday. So those in person will be doing questions using the catch box. I think we had some real team building moments yesterday throwing the catch box. But today, LOC members are a little bit more strategically placed along the aisle, so they will be able to stand up and help folks with the throwing of it. Just a reminder that the catch box is just a microphone to connect to those online. It does not connect to the speakers here. So you really need to project when using the catch box. Those who will be online, we've got our wonderful representing Montreal with the halves. Hand to be able to coordinate with them. And just a reminder to everyone to state who you are. We have a camera up here at the front, which is not yet working, but hopefully will be working. But if not, people online don't know who's speaking in the audience. So really remember to say your name. For speaker instructions, please stay near the computer. Catchbox and computer are the only 2 microphones. If you're a speaker, please wear this handy dandy headset, which we're not doing a very good example of right now, but it'll help people in the back be able to hear more clearly, but you still need to stay near the computer. The microphone only connects to these speakers in the room. It doesn't go back to the people online. And there is a clicker at the center of the room for you to use, but I would highly suggest you figure out how to use it prior to the start of your talk. Something fun we want to do, this is really inspired by John Fest at Stanford back in February of 2025, and it was a huge success, is to try to encourage crosstalk between those who are online and those who are in person. So it's a little bit of homework. So I really want to ask that everyone in person find someone who is participating online and just reach out to them. Maybe it's someone you have been interested in talking to for a while, but they weren't able to make it in person. And just send them a quick little message. Hey, I'm interested in this aspect of your research, and try to strike up a Slack conversation. And same goes for those online. Try to find someone in person. You can go ahead to the Slack and do it that way. Of course, you don't have to do it, but I think it would be a really, really nice way to be able to mix those 2 populations per se.
Okay, so the last thing is just on a code of conduct. We've outlined it in much more detail on our website, and so I encourage you to go look. But of course, the bullet points are: we should all behave professionally. We want to be kind to one another. Let's not insult or put down each other. We're all here to learn, and we will not tolerate any kind of harassment or discrimination. And if you're experiencing that, or if you're seeing anything like that, please approach us or one of the other LOC members, and we'll deal with it swiftly. Yeah, I think that's it. Oh, wait, one more thing. So if you need any help, you can post an FRB2025 general, and the LOC members are checking that all the time, so we should be able to get you the information you need ASAP. If it's something private, you can message me or Alice directly, and we can help. There's the email that's listed everywhere. And then from emergencies, like 911 is the real place to go, but if there's kind of just a McGill emergency, here's the security number. And with that, we will hand over to the session chair for today. Thank you.
Okay, good morning. I'm Mason. I'm a postdoc here at McGill, also one of our other team members, and I'll be chairing this and also the first population session. And as Amanda was saying, we now have, I guess, a quartet of speakers: Laura, Paul, Sean, and Jason. All 4 of you are, postdoc finalists, so I thought to do keep on time. So I guess we'll start with Laura. And then if everyone collected 5 minutes, before that. So without further ado, Laura.
Yeah, I know, I have to read it. Oh yeah, Shami, if you're online, can we hear you? Could you do a mic test?
Oh, yeah. Did you hear me okay?
Yeah.
I'll have one of you guys page through slides for me, probably Jason, since he's going to continue from where I leave off, if Jason's around. Or Paul can do it too.
Wow. Oh. Really? I think probably my ponytail eyes for the hair out of the way. All right. All right, so good morning. Thank you to the organizers for asking us to give, oops, I saved on the computer, sorry. A little bit of retrospective of the first repeater, known as 121102. I just had 10 years 10 years ago this year, we identified it as a repeater. So the way we decided to frame this, we sort of broke it into 4 topics, and we want to discuss some of the science that was enabled by NVIDIA of 121102's first. So I will begin by talking about the discovery, and then Paul will take over talking about the repeating source, and then Sean will take over about the localization, and then Jason will end on some of the properties of the radio properties of the source. And so the discovery, it was made by Arecibo, which was a first in the sense that it was the most sensitive telescope at the time, radio telescope at the time. It was also the first non-Parkes FRB and gave the first signs of the weird burst structure. And the first repeating source, of course, the 2, I think, main scientific results that came out of it is it immediately ruled out all cataclysmic models, at least for this source. The time that was with a big assumption that these were probably cataclysmic in origin. And it also obviously enabled a large number of multi-wavelengths follow-up. So one major follow-up was that we had the first arcsecond localization, which gave us the first host. It turned out we had the first persistent radio sources, and many other things happened. And then finally, of course, we then were able to, over the years, amass a large statistical sample and look at how the properties change over time, polarization, et cetera. We don't have time to go through all of these. This could be probably a 3-hour talk in and of itself. We will highlight a few of the key points. So yeah, I'm going to talk about discovery. So yes, of course, this was the first FRB found with Arecibo. Arecibo, for those of you who have only been in the field very briefly, was a 305-meter telescope in Puerto Rico. Unfortunately, 5 years ago, the collapse, this platform at the very top, unfortunately, it came unanchored, and one of the cables came unanchored, and this platform crashed into the dish. It was very sad for those of us who've been using this telescope for years, and anyone who's been there knows that it's a very special place. So the source was found in what was called the Pulsar Alpha survey. So P Alpha was a survey that used the Alpha receiver. Alpha was a 7-beam L-band feed array. And what we were doing was we were actually, the initial science of the survey was to do a low galactic latitude search for pulsars. And eventually we thought it would be a good idea to also do a single pulse search on these data. We found, of course, many RATs and whatnot. But the goal then became to also try to find an FRB. So it was towards the end of my thesis. What I did was I was tasked with doing a single pulse search on the data taken with this called Mach spectrometers, which was a 2nd-generation spectrometer. And I actually ran my search on the Atlas cluster at the Albert Einstein Institute in Hanover. And so Saturday, June 29th, I was sitting looking through some candidates one morning, and this guy popped up. So on the left, you see this was sort of my version of the Presto single pulse plots in sort of around second 129, I think. You can clearly see that sort of canoe-shaped event that turned out to be the source. This was my, at the time, on the right, a very ugly dynamic spectrum. I spent a long time trying to fiddle with the properties of the plot in order to get something to pop up at the bottom half, but it never did. So I sent an email to Vicky and Vicky Caspi, of course, and Maura McLaughlin, who are the two leads of the single pulse working group. And my mention of this candidate was the third paragraph of the long email. And so I think it took them a while to actually see that. So tip to students, if you have important stuff in emails, put it near the top. If you're writing supervisors who have a lot of emails to read. So so after thinking, and we finally convinced ourselves, yeah, this is something which is quite interesting. So some details about the source. It was found very close to the galactic anti-center and at very low galactic latitudes. The DM was 557 parsecs per cubic centimeter at the discovery. This was about 3 times as high as the galactic contribution predicted from NE 2001. And at the time, the way that people argued that these sources were extragalactic was saying that the DM contribution was way higher than you should get from the galaxy. In this case, I mean, 3 times higher is still quite a bit higher, but it wasn't as, certainly wasn't as clear as some other instances from parks. Maybe one fun historical fact that I'd actually forgotten until recently is that at very early days, what people like to do is actually measure the dispersion index. So basically measure the dependence of the sweep with frequency, because we know astrophysical dispersion from physics should be really minus 2.0. And so people did this as a way to convince ourselves and convince the community that these things were actually astrophysical, not some sort of weird RFI. And so at the time, this was still common. So we also did this measurement and we got that, yes, it was within the uncertainties, what you'd expect from astrophysical dispersion. But perhaps the weirdest thing was actually this inverted spectrum. And so one speculation was that, as we know, of course, the size of the beam changes across the observing band. And so if you're off of boresight, so if your source is not at the center, you can actually get an imposed instrumental spectrum from the fact that your sensitivity at that position changes due to the beam size changing. But to get an inverted spectrum instrumentally, you actually have to be at a rising edge of the side lobe, which is shown here in this instrumental spectral index plot over on the right. And you might think, well, it'd be very, very odd to have a detection of the side lobe, but actually it's worth pointing out that Arecibo side lobes had comparable sensitivity at the peak to GBT or Effelsberg. So it wasn't actually so unreasonable that we'd see it in a side lobe. Oh, yeah, the fun fact, turned out after the fact, it was actually detected in the side lobe. Once we localized it, we could confirm that it was side lobe detection. Off the top of my head, he asked what is the area of the side lobes compared to the main lobe? That's a good question. I mean, by eye, 2%. That's true. If you take in the instrumental spectral index, yeah, it was a very small fraction of the side lobe in general, of course, as a whole. Yeah. So it was actually, So it's a fair question. So yes, there is this inverted spectrum. So yes, it was found on the side lobe. So it could be some combination of instrumental and intrinsic. This spectrum. I don't think we ever went back and actually looked at exactly what the instrumental spectrum was, because it wasn't that interesting, really. I mean, scientifically, it wasn't worth putting in the time. But it is a fun fact that it was actually found in the side lobe. So immediately after this, and sort of around the first paper, we did some follow-up and didn't see anything. Here's some comments from the reviewers that we got for, I think, the DDT. And then we put in another proposal, a regular proposal, and things changed. You want? Yeah. That's right, because I start throwing stuff around and it's distracting. And I have to start off with my hair.
Yeah, so there's 4 of us with, varying abilities in time management. So yeah, better to wait till the end. Where I guess I came into the story is in 2015, this is where the state of the field kind of was. There were about 19 FRBs known at the time. 17 of them were detected at parks, 1 at GBT, and 1 at Arecibo. So we had convinced ourselves that, these weren't just a unique phenomenon to the parks telescope, instrumental, which is, an important aspect of the Arecibo discovery. And Parks had started putting limits on repeatability in follow-up with a paper led by Emily Petroff. And the GBT FRB had a little bit of follow-up done on it. And so we were doing our own follow-up on the Arecibo detected 121102. You know, in order to put good constraints on repetition, you really need to spend a lot of time on source. It's hard to do with single dish telescopes. You need wide field transient detectors, which, you know, CHIME has shown is very good at detecting repeaters, right? But so we were doing our, we spent, you know, a good amount of time, Arecibo time, following up on 121102. And so at the time I was a PhD student at McGill, you know, as Amanda alluded to, at a desk over there. And my job at the time, one of my jobs was running the search pipeline for pulses, for periodic you know, signals from pulsars, as well as single pulses from pulsars on the Gilliman supercomputer, which is in Montreal, not on the McGill campus, but at ATS, you know, over, I don't know, am I doing good with directions over there? in kind of in Griffintown. So at the time, you know, it's not like CHIME where we do real, you know, CHIME and other searches on, you know, on almost every radio telescope these days, or the major ones where we have real time and, you know, commensal searches. We had to search our data offline. So the data, you know, saved to disk from the telescope, made its way to Cornell, and then made its way to Gilliman. And then eventually I, you know, got around the data oddities because the scans were much longer than our survey scans, which, you know, when you design a pipeline, you don't make it flexible for some reason. And then, you know, so eventually the data, you know, got through Gilliman, and I guess I sat down at my desk at some point and decided to pull up the results on November 5th, which is an interesting day, right? Coincidentally, I guess Guy Fawkes Day, so we could write a remember the 5th of November poem. The many waterfall plots. And so, you know, what I saw was these a little bit busy plots, right? There's a lot going on. Most of this is noise and RFI. I guess we kind of set our threshold of what to plot here fairly. Did I advance already? I didn't mean to advance. Fairly low. But if you look at this plot over here, this is DM versus time. And you can see that this burst colored in black here is like, you know, above a signal to noise of 100. So these were, you know, bright repetitions. You know, so it was quite shocking to see these. I think I, you know, said something and then my office mates gathered around. Vicky was at a conference, so I couldn't summon her. But I guess, yeah, Ingrid Stairs was on sabbatical at McGill, so she eventually, someone summoned her over and we gathered around my my desk, which is no longer there. So on the tour, you'll see desks in there, but they won't be my desk. Sorry. Sorry, Amanda. I think it's in a landfill. Those desks were terrible and disintegrating. Yes. They got new, better desks for the students, much, you know, improved MSI or TSI. Okay, so gathered around, I decided to have some fun, maybe a little bit encouraged by the group of people standing behind me. And I entitled, I went understated with the email. So a minor point of interest regarding the Spitler burst. I wrote a little bit matter of factly in my language. I don't know if you can read the small text there. I did a period search, found something, it was 8 seconds. I think Daniela told us yesterday about the pitfalls of finding periods and small amounts of data, not taking into account trial factors or that. So that 8-second period didn't pan out. Yeah, there's perhaps it's an extragalactic radio magnetar. Well, we still don't know whether that's the case, but sorry. Yeah. And yeah, my colleagues were mostly, I think, entertained by the subject. And so I don't know if I have any tips on students how to write emails, but yeah. All right. So at the time in 2015, there were a lot of theories and for what FRBs could be. I think we had the refrain, which went until really Chime started detecting FRBs, was there's more theories than bursts, right? Although I guess maybe sources, because the repeaters were putting out lots of bursts. But the first thing we could do by discovering a repeating source was cross out all of the cataclysmic models, and I'll admit that I put together the crossing out a little bit quickly. So it's possible I missed some models, so apologies if I crossed out one that actually can repeat. Apologies. But you can see, kind of here that a lot of the models pre-2015 were, one-offs that, and then a lot more repeatery models are popular after 2015. So that was the immediate, implication of detecting a repeating burst. And the other thing that was peculiar to this source was that it had weird spectra. Jason will spend a little bit more time talking about this, so I won't spend too much, but these 3 bursts here are all, in the same scan, only a few minutes apart. And you can see one rising in frequency there towards high frequency, peaking in the band towards low frequency. These were wild. No one, had really, what we saw from pulsars and the FRBs detected at Parkes was they are broadband, mildly negative spectral indices. FRB2025 was a different beast. It was significantly wider than the other FRBs at the time. Our widths were something like 3 to 9 milliseconds. When we took a look at what Parkes had published at the time, taking into account their, propagation and instrumental effects, it looked like they were all significantly narrower than 121102. And so, there were hints right away there that differences in the repeater spectra, right? We, immediately had the question, as I think, you would, is do all FRBs repeat? And so, repetition rates are a function of the, luminosity function and thus the sensitivity of your telescope. And Arecibo's a much more sensitive telescope than Parkes, being 305 meters across. We were observing at the same frequency. Differences in frequency weren't a factor there. But a possibility was that all FRBs repeated, and Parkes is just seeing the brighter end of the these luminosity distributions for the bursts. Another effect that's kind of interesting when you do take into account frequency in the context of 121102 is that 121102 has still only ever been detected once in Chime. Our most prodigious detector of repeating FRBs doesn't have the repeater as a repeating source. And so that could be frequency dependence on the rate this was detected at a time when Arecibo was seeing a lot of bursts in what's called the November rain. Okay, the next thing we did was a lot of follow-up. You detect something exciting, the next thing you want to do is point every telescope you can get your hands on at it. So we of course did a lot more radio observing with Arecibo, GBT, Effelsberg. We pretty much immediately put in a TOO request to Swift to get some X-ray data on the location, as well as deeper X-ray with Chandra. And so you can kind of see it here is already the hints and the elusiveness of clustering of the bursts in the repeater. We had 8 bursts on one day there in June 2015, and then a lot of non-detections later. You can't see my, oh, you can see my, a lot of non-detections later, as well as the start of many non-detections with VLA that Johnny will talk about. We spent 10 hours there, no bursts seen in VLA, making our localization efforts complicated. So we started doing, we've got our first repeating source, so we start doing some high energy follow-up. Initially, our first observation with Chandra, we had poor localization, so we've got the original beam that detected the in red there, and then the 2 beams that detected the repetitions in yellow there, and green was kind of our I don't know, 90% confidence interval, and there were lots of X-ray sources there, and so we really needed a localization to get that. And so to jump ahead past the localization in the story, which Shami will talk about next, once we got the localization, we were able to see there's no X-ray source there with Chandra. We had 40 kiloseconds of Chandra there, 2 photons. I think Shami gave them names. I don't remember what they were. I don't know, Kevin and Fred, I don't know, maybe he would know. Yeah, and so the next thing we did in terms of high energy was not just observe with Chandra and XMM, but do it simultaneously with a radio telescope. So this was our first time observing simultaneously in X-ray and radio of a repeating FRB source. And so we got in January, in September and January of September 2016 and January 2017, so shortly after the VLA localization, quite a bit of time to observe simultaneously. We detected many, say a dozen radio bursts and no X-ray bursts, allowing us to put limits on what could be there. And the limits, especially given that it's a repeating source, they're my limits, so maybe I can say they're not that interesting. Maybe I shouldn't put myself down. But, they rule out GRB-like energies, which I think we were pretty sure there wasn't a gamma ray burst going off every time there was a repetition of this source. If you were generous, you could say the limits were around the level of the brightest giant flares we had seen. But most bursts from magnetars and accreting sources in our galaxy, that we know of, were well below these limits. But in the intervening 10 years, we've done, we've improved on that a bit. We've got now, or have had for a few years, a repeater in M81, of course, much closer at 3.6, not parsecs. The slide says parsec. It'd be wonderful if we had an FRB source at 3.6 parsec. Okay, 3.6 megaparsecs. Compared to about a gigaparsec where 12.11.02 was. And that's allowed us to push down to, just kind of starting to skirt the top of the energetics that we see from, the normal bursts from magnetars and accreting sources in our galaxy. Okay, so I jumped ahead of the localization a bit, but now let's talk about the localization in earnest with Shami. So take it away, Shami. Maybe.
Awesome,
Can I get
thanks.
your
Can you guys
video?
hear me okay? And
I will
yes,
advance the slides.
yeah, can you hear me okay?
We can
Yeah,
hear you.
good.
We'll just
All
take
right.
a second to get your face on the.
Yeah.
We can hear you, Shami. We'll just take a second to get your face on the presentation, if that's fine.
Okay. And then Paul, yeah, or Jason, if one of you can move the mouse for me, there are 2 slides where the mouse is going to be important.
Yeah, I'll stand here, Shami, and advance the slides.
Okay, thanks.
Oh,
So let's
Next,
do,
click it into presentation mode.
yeah, 1 second. Where's that little bar? Put what back to full screen? I think we should do it like this. Yeah. Yeah.
So play from start. But
Oh, we'll just advance really fast. It's an old computer.
okay. I will advance to Shami.
And the wrong version is being shared online.
Ah, yeah.
Why is it so small? How's that?
Yep.
Okay.
Very good. Well, thank you all.
Great.
And thank you especially to the organizers for putting this together and having us talk about this little bit of history. And I'm really very sad not to be there in person, but we'll manage online. So just to pick up the story on the next slide, immediately after Paul sent around this is a repeating source email, the very first call that we had, there was a discussion that, okay, if it is a repeating source, it's possible that we can do interferometric localization. Can we go on to the next one, Paul? Yeah. And it was clear from Paul's detections that the original detection from Spittler et al. Was apparently in a side lobe. So the white circle is the original detection. The other white circles are the redetections that Paul showed. And so we had this generous uncertainty region, which is denoted by this yellow circle on the map. And in that, there's obviously many dozens of sources in a VLA image. And so the prospect was that if we could pinpoint it to one of these sources or something else, who knows, we could do some real science with the host galaxy and stuff. So we were very excited. The repetition email was on November 5th. I went back to look at it, and the VLA proposal was submitted on November 12th. It ran into some controversy because what we were proposing would have run the VLA correlator with an output rate which was at that point extraordinary. It was 1 terabyte an hour. These days, everyone, of course, is like, yeah, okay, a terabyte an hour. But back then, that was truly, truly extraordinary. It was more than 10 times the typical VLA data rate at that point in time. So it did get on Sky on November 25th. And then as Paul showed, next slide, please. We were going to take fast sampled visibility data. And so again, these days, this is a standard way of operating. But back then we were saying, oh, we will do two complementary approaches. One is we will basically synthesize beams that tile the VLA field of view. And then for each of those beams, we're going to do a standard single pulse search. So we would use the UNV data to make an image and then search for the pulse in time and dispersion measure. And at the same time, we were going to do a complementary approach, which is we were going to de-disperse the visibilities, taking out the UV, taking out the DM dependence in the UV, and then invert it as a function of time to make millisecond images. And at this point, I should say, Casey Law and Sarah Burks-Polar and Jeff Bauer and Paul Demarest, they'd been working at the VLA for a long time to deploy the RealFast system, which was going to do this millisecond imaging. And eventually, over the course of this project, it developed into a collaboration with all of them, where they were running the RealFast pipeline to do the millisecond imaging. And then after the fact, we were using the UV data and creating beams and extracting at each beam position a pulse search data set. So on the next slide, we ran into some really unfortunate luck. Basically, we had no detections in 10 hours. Look at that long string of zeros in the column that I've highlighted. We went back and asked for 40 more hours. And the VLA was like, well, it's a lot of data because this is all going into the archive and for nothing really. But they gave us 40 more hours. We had no burst detections in those 40 hours. And then the next 40 hours that we asked for was really somewhat seriously controversial. After the fact, I've heard from people at NRAO that it was internally controversial giving us that time just because we weren't seeing anything. But luckily, in our second swath of 40 hours, so at like 52 hours of observation, we got a burst detection. And then we just got a whole string of these bursts. So on the next slide, you'll see what the sky looks like in one of those 5 millisecond images. And I've included those two intersecting circles of the Arecibo detection for reference. And it's very clear that in that 5 millisecond image, this FRB is the only source. It's the brightest by far source in the sky. And on the next slide, when we phase up the beam at the position of that burst, we just see this beautiful dispersed trace. This was work that Robert Wharton, a graduate student here at that time, did. It is absolutely spectacular. And so now on the next slide, we finally do have exactly where this burst is coming from. And it turns out, somewhat unexpectedly, it was this nondescript compact point source. And so this was a huge splash. It was on the cover of Nature as the mystery object. This is the first time the VLA itself has been on the cover of Nature just because our source was not very spectacular to look at. But next slide, what is this little point source doing? Next one. Yeah. So the black dots here, now that we know which source is the relevant source, we can go back through all 83 hours of our data and look at what that compact source was doing. And it was just basically bubbling up and down, somewhat variable, just like a typical radio AGN or a general compact radio source. So it was the red triangles in that plot show when at the epochs at which we detected bursts, and at some epochs we detected a couple of bursts. And you can see that the brightness of this compact source is completely uncorrelated to whether or not we were detecting bursts. So there was this initial idea, what if this persistent radio source is actually the superposition of hundreds of sub-threshold bursts? And we convinced ourselves that that was an unlikely idea, that instead it was likely to be possibly a pulsar wind nebula supernova remnant, possibly an AGN. And I think what a persistent radio source is remains to this point. Basically, those options all remain open. So it's interesting. I also want to point out how unlucky we were with the scheduling. all of these epochs with non-detections until we weren't. Like every epoch at that point, we got a burst. It's another hint at the sporadicity of this source, which comes back to be a part of the story later on. So next, please. Yeah, this was followed up with EVN and Arecibo with VLBI, and Benito Marcore led the sub-milliarcs or milliarc second precision localization, from which we knew that the bursts and this persistent radio source coincided to better than 12 milliarc seconds. So within 40 parsecs of each other, we localized it. All right. Next one. Yes. So now the question is, now that we have a precise localization, as Paul has already pointed out, we can observe over a broad range of frequencies. We can get simultaneous coverage at radio and X-ray, gamma ray, optical. Possibly, we could get multi-wavelength counterparts to the bursts. And we have a good handle on what the energy of the burst is if we can get d gigaparsec constrained. So let's go on to the next slide. We did a whole bunch of multi-wavelength follow-up. So at the VLA at 3, 5, and 10 gigahertz, we could see the persistent radio source that was not visible in ALMA. There was nothing in various optical surveys or in H-alpha surveys or in X-rays, except in an archival Keck image, there's a little smudge there. And that little smudge really got us interested. We had a TOO proposal at Gemini that Sriharsh Tendulkar led. Next slide, please. Yeah, that's the little smudge in the Keck image. It's suggestive. It's suggestive that there is something there. So in the next slide, I'm showing you the Gemini image. And there it is, the host galaxy for this FRB, right exactly where the interferometric position had localized it to. So it's a 25th magnitude source, really at the end of the reach of these big telescopes. It's a dwarf galaxy. And the first thing we asked Sriharsh said, oh, we have a spectrum. We were like, well, is there a redshift? Is it actually an extragalactic source? And the answer was yes. I love the spectrum that I've shown at the bottom of this plot. The slit is placed, if Paul can wave the mouse around, the slit is placed across the host galaxy and the two stars below it. So the two stars and the host galaxy make sort of a straight line in that inset, Paul. Yeah, those two stars and that host galaxy. So the slit is placed right down those 3 point sources. And you can see the stars are broadband, so they have these smooth spectra at the bottom of the page, while the host galaxy just breaks up into these very bright emission lines, which are uniquely H-alpha, H-beta, oxygen lines, and sulfur lines. It's a definitive redshift of 0.193. And this, I think, was the absolute slam dunk confirmation that yes, these FRBs are extragalactic sources. The distance is about a gigaparsec, and we now have an energy of these bursts of about 10 to the 38th ergs packed into this 0.1 Jansky millisecond burst at a distance of a gigaparsec. On the next slide, Case Basa and others led HST follow-up of this dwarf galaxy. And we could see immediately that the host galaxy broke up into this bright compact knot of star formation that's visible in there. And it's suggestive right there of a connection to superluminous supernovae and long gamma ray bursts. And again, pointing towards magnetar models for this one source. All right, I will hand off here to Jason to talk a little bit more about the environment and the wacky bursts for this source.
All right. Yeah, so I'm going to say a little bit about the burst mission, and kind of some of the main points that I wanted to make here is, you know, when you're seeing something for the first time, it's kind of more difficult to understand what's going on. So for the students in the audience, maybe there's like some lessons here. You know, after we found the repetitions, some of the bursts and whatnot, obviously we tried to get better data on the source. We wanted to get higher time resolution. We wanted to get polarimetry. That meant we moved from like one data recording machine to a different data recording machine. And I spent like some of the weekend going through like thousands and thousands of emails that I have in my inbox from 12/11/02 days. I think there's something like 4,000 or 5,000 emails about the source. And going through the various threads, I found one thread where I was emailing Paul Demers and Scott Ransom about like, we're getting these new observations of the source, and I'm making these single pulse plots, and we see a lot of artifacts in the data at a DM of 557, which is exactly the DM of the source, and it had me like freaked out. And it kind of reminded me that I didn't sleep very well that night. Yeah. You want to move Shami out of the way? Oh, sorry, Shami, you're being degraded. Yeah, okay. Yeah, and so there was a little bit of discussion about this, a little bit worry about what is going on here, although we're still fairly confident that the source hadn't suddenly disappeared. But then I started, for the first time, I started plotting up what the bursts look like as a function of time and frequency with this improved data. And I remember seeing this plot for the first time and thinking like, uh-oh, I think we have a problem here. What is going on with the data recording machine? Because the data was supposed to be de-dispersed already. And yet you can see this like sweep through the data. This is not at like optimal time resolution. And I thought like, oh, either the dispersion measure is now suddenly jumping around. I was kind of thinking at the time, has it jumped up to one of these other peaks that you see in the middle plot there? What is going on here? What is this notch through the data? And there was some concern about that as well, whether the data recording machine was broken, or if we were looking at some kind of really weird source. And so I sent this around to people in the collaboration. For instance, one of the emails I got back, this is an email thread that started with, is FRB2025 really not a flare star? Because some of you might be remembering that some of the very early models for FRBs was this idea that maybe the dispersion is not dispersion at all. It's actually like delay in the atmosphere of a star, maybe like a flare star. And these strange bursts that we started seeing, which are shown here from one of the papers that we published on this, really looked a lot like these kind of like drifting patterns that you see sometimes from like solar bursts or from flare stars. So there's a lot of discussion about this, also about like how do we actually de-disperse bursts when they have these weird shapes, and what kind of emission are we seeing? And like a lot of people chimed in about, well, this is just not the type of stuff that we see from pulsars or from magnetars. And we now know, this is kind of a talk about the various bursts that we've seen from the source. So that was kind of the first example of the so-called sad trombone effect. Now we've seen that this is kind of a characteristic of many of the repeating sources. Ziggy had a paper showing that there's this kind of characteristic difference between repeaters and non-repeaters. This is also the source, it hasn't been mentioned yet, that we've detected up to the highest radio frequency thus far. And that's enabled also some interesting studies showing that this source can produce bursts that even last for only a few microseconds or so. It kind of suggests that, we've really just scratched the surface in terms of searching for fast radio bursts with the telescopes we have. But maybe one of the most astounding things, and Laura and I were talking before the talk this morning, we really should highlight also Andrew Seymour's contribution to this work, in addition to Danielle Keely's contribution. One of the most outstanding things that came out of the follow-up of the source is once we started getting really high quality data also at higher frequencies, thanks to Andrew's work of implementing a new observing mode at Arecibo, we realized that the rotation measure towards this source is also absolutely enormous, and the source is highly polarized. So we spent like several years trying to get detections of polarization with the L-band data we had, and we couldn't see any polarization at all. And I remember like Daniele was in my office in Amsterdam. We were just having our kind of weekly meeting, and he was searching for rotation measure signature in these high frequency data we got from Arecibo. He searched, he saw nothing. He searched again, he saw nothing. We were just chit-chatting about various other things he was working on. And I said, well, why don't you just search out to like 300,000 or something like that? Let's just, this is our last attempt to try and get polarization from the source. And we were just chatting, and the computer's plugging away, and all of a sudden the plot comes up and he shows it to me, and we both like sweared and said some nasty words and holy crap, and there was a whole, there's not enough time to get into it. There was a whole discussion about whether this was real or not, or whether this was also some kind of instrumental artifact. But with detections from the GBT and various other scrutinies, we realized that this was a real deal, and now it's been confirmed with a few other FRB. So the last thing that I was going to say is, this source has really been a boon for for FRB science because it's also, as Paul emphasized, it's allowed us to actually see how sources change with time. And so not just Arecibo, but also GBT and FAST and Effelsberg and the Nancy radio telescope have been showing us how the rotation measure and dispersion measure of the source have been changing with time. And there's been tons of papers about modeling that. There are over 2,000 detected bursts thus far. And really, like, you know, as Laura will summarize in the next few slides, and we're almost done, don't worry, Mason. Yeah, it's really been an amazing source for understanding fast radio bursts.
All right, so I'm gonna wrap it up. Some conclusions. So Jason added this list of the 10 most cited, 10 most cited papers on the source. I think we've mentioned most of them. Here's some statistics. I think perhaps one that I'd like to highlight is that if you put 12802 into the ADS abstract search, you get 276 papers, which have been cited collectively 15,000 times. So what I'd like to point is that although the four of us are here talking about this, it has really been a group effort in the community. Many people have published work on this over the last 10 years. That said, we still don't know what it is, but hey. So very quickly, final lessons learned. I want to formulate this a bit from the point of view, some of the assumptions that were broken with this discovery. Yeah, so discovery was, I think this was really the final confirmation that FRBs were astrophysical. I think our Parks colleagues really convinced us probably 97% of the way there, but I think this Arecibo detection really was, okay, it's not just a weird Parks phenomenon, these things are astrophysical, so let's have the field explode. And again, the first repeating source, I mean, it really broke the assumption of everyone that these are from some cataclysmic origin. And I think a lot of the theoretical work then shifted over to models which also included the possibility of repetitions. And I mean, obviously we went on a lot about how the multi-wavelength follow-up was really significant. It was also the first, of course, FRB host and persistent radio source. And looking back on it, for me, what was really interesting at the time is that a lot of the data, so the repetitions, the host galaxies, you heard the first day being the host of Superluma supernova, this persistent radio source, it fit in this huge RM that was highly variable, fit perfectly into this model of you know, the millisecond magnetar that's maybe a decade old, that's you know, super energetic and feeling this nebula. And I mean, it fit perfectly. So we thought for a couple of years, maybe a year, we thought maybe we had FRB solved until of course, our colleagues in Australia and in California found localized a few more FRBs, and suddenly the host galaxy was completely different. So I wanted to quote Wenfei Fong here, who gave a really nice talk I saw on sort of to FRB people on lessons learned from the GRB community. And one thing that I took from that was that the first sample of a population is weird. And in this case, I think the first sample of the population was a bit weird. We have some other ones that are similar, but certainly is not super representative of the entire field or entire population of FRBs. And in terms of the radio properties, I think the one assumption that this source really broke in our heads was this narrow band emission, or the emission fraction, delta nu over nu was less than 1. I think a lot of people assume, because you're coming from pulsar community, that the emission is going to be a broadband, it's going to be wider than our receiver bandwidth, and if it isn't, then it could be some sort of weird RFI or whatnot. I think that's something that's really broke. I think one assumption that we really broke in terms of understanding both from the mission physics point of view and theory, but also from writing software that finds these things. It's important to take into account that your burst might not be emitting over the full band. So I was asked to just give my thoughts on what I think this source might be. So it's been 10 years. We're still not 100% sure. I'm not really a betting person, but I think the safest bet would be this probably a neutron star. Personally, I think, again, this picture of it being sort of a young millisecond magnetar fueling the nebula, I think really works well for this source. Of course, how applicable that is to the rest of the population, I think is not super obvious. So if you look at this source with the entire population, I think it's suggesting that the universe is creative, astrophysics is complicated, and there's probably many ways or many flavors, many stages, many channels in order to get fast radio bursts. So that, I guess, makes it fun. With that, I will conclude, and take any questions. Maybe my other colleagues can pop up if anyone has questions for them. And yeah, thank you again for inviting us. Tell me that.
Yeah. Okay, so Greg, if all four o'clock, yeah. Could the LOC help me to stand up so that I can pass the catch box around? So questions. So Brian. Is it Brian?
This is Brian Gainsler from University of California, Santa Cruz. Question perhaps for Laura and Paul. Knowing the rates that we now know from, say, FAST, how many FRBs should have P alpha have found? And I'm assuming you only ever found one, right?
Calculation?
Yeah, there was a second Arecibo FRB, you know, in Patel et al.
Yeah.
Some year.
And is 2 what you would have expected?
That's a good question. I have not done the number. We done the number?
Can I,
Vicky urgently looks like she wants to speak.
yeah, I was going to say, remember, it's a survey of the galactic plane. So the numbers we weren't expecting that many, and it's 121102 was found in the exact anti-center pointings that we had.
I think so. So yesterday the statement was the projected all-sky rate from FAST was a order 10 to the 5, and I think our projected all-sky rate was also 10 to 5, if I remember correctly. So I mean, in that sense, they're consistent. Yeah.
Vicky, you want the box? Really clarify.
I was on the basketball team in high school. In Arecibo, it's the initial detection was quite bright, and the Patel et al. Source was really, really faint, right on the edge of detection. We hemmed and hawed about if we thought it was real, and it was a little surprising that there was nothing kind of in that gap. But you know, yes, it was galactic plane. So I think we were a little surprised we didn't find 1 or 2 more.
Any questions online? No? Okay. Anyone else in the room? Okay. If not, we can just conclude here for now and thank the 4 speakers again. So now we move on to the next session, populations. We'll just start off very, very appropriately because we just had a great long initial start to the repeating FRBs. And now we'll have Sloan Sirota from West Virginia University, who will actually maybe try to attempt the question, do all FRBs repeat?
Here's again. Was it the PowerPoint or the Google Slides? Have to reshare it, and once you're set up, use the microphone. All yours. Um,
Okay, can everyone hear me? Okay, great. So as Mason just said, I'm Sloan Sirota. I am a PhD student at WVU, and I'm here to talk to you about my work, trying to answer the question, do all fast radio bursts repeat? Now, they, in the last talk, they gave a really great background about R1 and, you know, talking about They also mentioned the question, do all FRBs repeat? There are some people that say yes. There are certain progenitor models that could account for both repeating and non-repeating, or that could account for repeating sources and non-repeating sources being the same. There is some analysis that has shown some type of link between their energy distributions. And also, there is the big question of, maybe this is just an observational bias, the fact that we're seeing so many differences between the two populations. On the other side of things, we have people who say, no, they're definitely not the same population. Hyperactive repeating sources are a very big argument on this side because, how do you account for both hyperactive sources and these so-called one-off sources coming from the same place because they're exhibiting such different properties. Machine learning algorithms that are, or blind machine learning algorithms have classified them as two separate populations. So that's just based off of statistical testing. And there have been many, many papers that have shown that there are distinct morphological differences. This being said, there's still a very, very large debate around this topic, and we're still trying to get to the bottom of this. So, following the analysis done in Yamasaki et al., a paper published in 2024, I'm attempting to shed some light on this question. So first, we're going to infer the chime selection function, which I'll get into in a minute. Then we're going to assume a power law burst rate distribution. Then, of course, we run our simulation. And then after that, we're going to see, okay, did it work? And then we're going to talk about the next steps. So first, we're going to infer the chime selection function. So I do want to give a disclaimer. This is not quite as in-depth as the talk that you will see from Kyle. I believe he's 2 more talks after me, so you'll get a bit more information from him. But we are attempting to find a simple yet still rigorous way to account for the chime sensitivity and chime exposure as a function of declination. So first, we assume a uniform all sky distribution. We assume that, everywhere in the sky, same number of FRBs. And we assume that it's a constant number of FRB sources in the chime sky. These assumptions are important. These are foundational assumptions in this analysis. And then we can compare this with the chime detections. And then from there, we can plot the chime detections as a function of declination. Now, we know that the chime sensitivity and exposure both scale with declination. So we compare the chime catalog 1 detections with what we would expect to see from a uniform all sky distribution. And out of this, we get what we call the selection function. The selection function is basically a measure of the probability of the chime telescope detecting an FRB given its declination. So that plot all the way on the right shows you what we get out of this analysis. We are using a polynomial fit. And so this is how we scale our simulated FRB detections. So now we need to figure out, okay, we have this scaling that we're going to use. So what about the burst rates? How do we determine that? So following Yamasaki et al., the paper I mentioned before, and Gardinier et al. In 2020, we will assume a power law burst rate distribution. What this means is the number of sources with a given repeating rate scales as that repeating rate with some power law index that is one of the parameters we're trying to find. So the repeater rate we take as bursts per hour. In that top plot, I show one of the plots from a chime paper on repeaters to show you that these burst rates kind of range from a max of like 10 bursts per hour, and they go down to 10 to the minus 2 bursts per hour. To kind of give you an idea, we're working in log space here. So now we have our burst rate distribution that we're going to now use to simulate our population of FRBs. So now we're going to run the simulation. So our simulation, we're trying to fit for 3 parameters, the minimum repeater rate or the minimum burst rate that a repeating source can have. We call that R min. We were also fitting for R max, which is, the maximum repeating rate that a source can have. Except we found that it makes just about no difference in the range where you would expect R max to fall. So we just set it to an upper limit of R log 10 of R max equals 1, aka 10 bursts per hour is the maximum repeating rate that you can find. And then we're fitting for that power law index that I mentioned. And then we're also attempting to fit for the number of FRBs in the chime sky. So unfortunately, I wish that I had a better set of results to show you. Anyone who's ever run an MCMC knows that this is not what a trace plot should look like. Anyone who hasn't run an MCMC, let me tell you right now, that is not what it should look like. What you're usually looking for in these trace plots is for all of these little walkers, all the lines to converge to one point to show you that your model has settled on one set of parameters that is the best fit for your whatever you're trying to fit. So unfortunately, in time for this talk, I was not able to get a set of parameters that my fit would converge to. However, it's okay because we can still look at kind of the average of these. I am giving you guys the disclaimer. This is not something that this model converged to. I'm giving you the average of where all these walkers are kind of landing. So don't ask me for like chi-squared or anything. It's a touchy subject. So can we find values that match the chime catalog 1 data? So I'm giving you the, once again, in quotes, best fit parameters. This is where our walkers kind of land. As you can see, we have a relatively good match for the chime parameters or the chime catalog 1 data, with the top lines being the total number of bursts that we see, the blue line being all of the repeating bursts, and the orange lines being all of the first repeats. So the first time we've seen each repeating source. The dotted lines are the simulated values, where the solid lines are the chime values. So a plot like this kind of shows that the lack of convergence is not necessarily due to the fact that, this is just a terrible model. So obviously the lack of convergence is never a good sign that your model matches whatever data you're looking at, but it's highly likely that there is an issue in the way we are calculating our log likelihood, something that I'm working on. But if you look at, once again, if you look at this plot, it shows that there is some merit and there is some hope for this model, and the fact that one day it will converge. In fact, if these are the parameters that don't converge, just imagine how good it'll look when they do converge. So this would predict approximately 100,000 FRBs in the chime sky. And also the R min value, I know that 10 to the minus 4.8 bursts per hour doesn't really make the most sense. You don't think, yes, 10 to the minus 4.8 bursts per hour, I did the math. That would be 1 burst every 50 or 60,000 hours. So that would be the lower end of our repeater rates, just to give you kind of a sense of the scale that we're working with. So now, next steps. Obviously, next step number 1, we're gonna fix our likelihood function so that it doesn't keep getting stuck. But as you'll hear in the next talk, there's a lot coming with chime catalog 2. So a huge thing to look for would be, does catalog 2 follow our fit parameters for catalog 1? So if that matches, that would give a lot of merit to the idea that, maybe this is just one really big population of all repeating sources. Another thing that we are going to do in the future is maybe look at different burst rate distributions. While, we could argue that they might all repeat, we could then say, are we drawing from the correct distribution? We could look at instead maybe a log normal distribution, which has been used in other analyses. We also, I forgot to mention, sorry, we use a Poissonian wait time distribution between our simulated bursts. This is not necessarily what is observed for all bursts. A lot of bursts do assume a Poissonian or pseudo-Poissonian wait time distribution, so the time that you see between repeat occurrences, but some have been better fit by a Weibull distribution. Some exhibit some type of burst memory. So these are all things that we might further incorporate into our simulation. And finally, the question of the hour, do all FRBs repeat? I wish I could give a more satisfying answer than maybe. So thank you, and I can take any questions.
Hi, Sloan. Great talk. I'm Kyle McGregor. I'm a master's student here at McGill. I was curious if you account for like fluence incompleteness at all, because there's this theory that the apparent one-off bursts could just be the brightest bursts from repeaters that have some energy distribution that we're only detecting the high tail of. So do you account for like sources that could emit bursts of too low energy for us to actually detect with chime?
Great question. So we actually kind of, in a way, sweep under the rug like fluence information and the energy distributions, because we're not assuming anything about morphology or anything. We are saying this is the number of sources that are visible to the chime sky. They repeat at this rate. We have at one point we have like a random number generator to kind of mimic that like randomness of the detection. But we don't directly take into account anything like signal to noise, fluence, anything like that.
We'll move on to a question from online.
Thanks. So I'm gonna, this has been written in the chat from Aniket Prasad. Hello, Sloan, excellent work there. I was curious about the plot of simulated versus FRBs. I see an abrupt looking jump around 1200 hours for the first repeat, sorry, the orange dotted line. Is there any physical reason or simulation assumption behind it? The total FRB's dotted line also shows a similar sudden jump.
Great question. There is no reason necessarily that we would expect that jump. The jump is likely a statistical fluctuation because some of the runs don't have that jump, some do. I thought that this was a good plot to kind of represent overall the model. So if I showed, I could pull up another plot and it wouldn't necessarily have that jump. I think it's a bit of a weird coincidence, but it does come up every once in a while.
Thank you.
Hey, Barak Zakai asking. So the original argument about whether FRBs repeat or not was better articulated by Shri. You can't kill a star for an FRB. The rate of FRBs is larger than the rate of forming stars. And it seems that it was missing from the discussion in. So maybe can you relate to this? Are we still talking about this?
Sorry, could you repeat the question?
Okay, I'll try to phrase it sharply. What is the all sky rate of FRBs above some, you define the fluence, and is it larger or smaller than the rate of, let's say, supernova or something?
Yeah, I can't comment on that. I've not, I don't know the all sky rate of supernovae or star formation. I also don't know that these parameters are necessarily the best ones. So I think that once we get our fit to converge completely, we would be able to say more about like the total number of FRBs in the sky, the all sky rate, because I think that this is kind of just trying to show what we could get out of our fit. But I don't necessarily know that 100,000 FRBs in the sky is, you know, where we're going to settle. Does that answer the question?
Okay, we'll leave it there for now. Let's thank Sloan again. Okay, and next we have Naman Jain, who's a student here at McGill, who will be talking about the, well, let me wait for the slides to pop up first. Also, I encourage folks, if you have more questions for the speakers, feel free to just ask in the Day 2 Slack channel.
Sorry, this is yours, eh?
Yeah.
Wait.
Is the screen shared appropriately?
I think so.
Okay, very good. Okay, so the next talk will be by Naman Jain, a student here at McGill, who'll be talking about the second Chime FRB catalog.
Can everyone hear me? Okay. So my name is Naman Jain, and I'm a master's student at McGill. And I'm here to present the second catalog of fast radio burst on behalf of the whole Chime FRB collaboration. One way to tackle the physical enigma that are fast radio bursts is to collect a large sample of bursts and then hopefully use that sample to answer some of the fundamental questions that were mentioned in the previous talks, such as what is the FRB luminosity function, whether or not all FRBs repeat, are there different classes of FRBs within the population, and what is the volumetric rate of FRBs. It's also having a large population is also useful in identifying unique FRBs that stand out from the general population, and also can be used to retrospectively cross-match with other transient catalogs to find multi-wavelength counterparts. Ziggy Plunis yesterday gave a great talk on the Chime FRB instrument. I want to highlight again that Chime is a great FRB hunting machine, owing to its large field of view of over 200 square degrees. It also observes about a wide bandwidth from 400 megahertz to 800 megahertz, and it observes the entire sky above a declination of -10 degrees every single day. And that allows us to see a lot of FRBs. In catalog 1, we presented 474 non-repeating bursts and 18 repeated sources observed between July 2018 and July 2019. In catalog 2, we have increased this number by an order of magnitude, and we're going to be presenting 3,649 apparent non-repeaters and 83 repeating bursts, a sum total of 4,547 bursts observed between July 2018 and September 2023. So what do we provide to the community in the upcoming data release? For every single burst, we will be providing a total intensity dynamic spectra from 400 to 800 megahertz, with a time resolution of 1 millisecond and frequency resolution of 24 kilohertz. We also provide localization estimates, typically within 10 arc minute. Note that the localization regions are quite complex, but we do provide the full confidence intervals. We also provide the detection signal to noise ratios, burst cosmology models that include parameters such as burst width, scattering time, spectral index, amongst others. We also provide the sky exposure for each sky position and fluence and flux limits, fluence and flux measurements, as well as instrument sensitivity to each burst in the catalog. A bit about exposure. For CHIME FRB, the exposure is defined as the total time each sky position spends within full width half maximum of CHIME beams at 600 megahertz. When calculating exposure, we exclude periods of system shutdowns or reduced sensitivity. Over the catalog 2 time period, the system uptime was about 76%. In the plot here, I'm showing, the plot here shows exposure as a function of galactic coordinates, and a typical sky location in the field of view has about 100 hours of exposure. Note that the regions above a declination of 70 degrees are circumpolar, and so we observe those twice a day in 2 different transits, and we code an exposure for each of the transits separately. The exposure also varies as a function of declination, with the north celestial pole having exposure of up to 10,000 hours in total. On average, CHIME observes about just under 2 sources per day with a signal to noise ratio of above 10. In the plot here, I'm showing the number of sources per day observed as a function of time bin by the month of the year. And we see some variability over here, and that's typically due to system shutdowns, updates, weather, or RFI environment. We have also done significant amount of consistency checks to make sure that other factors are not affecting the source rates. So for example, time at which the burst is detected, weeks, months, but the most significant contribution, or the most significant dependence, was on galactic latitude, which although I would note that latitude-dependent observing effects, such as system temperature variation or galactic DM, have not been corrected for here. We also provide burst properties, like flux influences, because we assume that because we assume in this calculation that the burst is observed at the bore site. These are strict lower limits, and any analysis using fluxes influences should take that into account. We also have not been able to provide flux influences for about 400 events due to calibration or RFI issues. And we did some consistency checks to make sure that this does not introduce biases into future analysis using this data. And we find that bursts with missing fluences tend to be a little wider and highly scattered compared to the general population. We also see morphological differences that were reported in Clutis et al. In previous work based on catalog 1 sample. More specifically, that repeating sources tend to have narrower bandwidths and larger burst widths. On that, there's a lot of ongoing and planned projects using this data. To highlight some, we are going to be soon also providing full baseband data for a subset of this sample. There's also going to be a new repeater catalog. A big shout out to Kyle McGregor, who will be talking about the CHIME FRB selection function in next talk. And I would also encourage people to look out for talks by Lodrick Kahinga and Swarali Patil on constraining M31 DM contribution and spatial dependence of FRB detections in the CGM and correspondence section on Thursday. as well as some work done by Vishwangi Shah on characterizing the lower bound on maximum FRB energy, and Hao Chang Wan on galaxy power cross spectrum. To summarize, the second CHIME FRB catalog presents the largest uniform sample of FRBs to date. The data release includes raw intensity data as well as various burst metrics. We observe roughly 2 FRBs above signal to noise 10 every day. And we have done a lot of sanity checks to characterize biases that may influence future analysis using this data. And I would like to emphasize that this is a collaboration-wide effort that took a lot of teamwork and perseverance to get this data out to the public. Thank you, and I'll take any questions.
Pick the one in front first.
Thanks for the really interesting talk. I'm Pavan from Swinburne. I was just curious about the number of candidates in the subthreshold region. If, for example, you have so many sources, how would that scale above a SNR of, say, 8?
I'm not sure if I know the answer to that, although, yeah, I'm sorry, I don't know the answer to that.
Kelly Gordy from CSIRO. Looking forward to seeing the results from this. Really nice. I was wondering whether the instrument or the search pipeline or the detection pipeline has changed significantly from the first catalog. Because I'm wondering, for certain statistical analyses, whether this can be combined with the first catalog or whether there's some caveats.
So there were some changes to the RFI sifting algorithm and de-dispersion algorithm in the system. I don't remember on top of my head when that happened in this timeline. But also there were changes made to the fit burst model. And there's elaborate section in the paper discussing how that, this is not the latest slide set, but there is an elaborate section in the paper that discusses how that update to fit burst model affects parameters like spectral running and spectral bandwidth.
Okay.
Oh, yeah.
Oh, okay. Okay, so you've gone and reanalyzed.
Oh, yeah. So the new catalog includes catalog 1 burst as well.
That's important. Okay, thanks.
Any other questions? One quick question, Marcus.
Hi, Marcus Lower from Swinburne University. This is awesome work. Could you say a little bit more about the morphological features that are being included in the catalog, aside from just widths and spectral indices?
So we have burst width, scattering time, DM, best SNR, spectral running, spectral index. Those are on top of my head.
Awesome, thanks.
Okay, we'll leave questions there and let's thank Naman again. Okay, the final talk of the session is by Carl McGregor. It's a 3+2 talk. I'll give you a 1-minute warning, not a 5-minute warning.
Thanks. Yeah, just 1 second to get the slides up. It was open one of the. That's not you, is it?
No.
Just a second, we might need to get his slides up again.
At the top.
Yep. Yep.
Spoiler alert, geez.
Great, yeah. Carl McGregor is a grad student here at McGill, and he will talk about selection function.
Thank you. Yeah. Perfect. Yeah. Yeah. I'm Kyle McGregor. I'm a master's student here at McGill. Yeah. Thanks for the shout outs in the previous talk. I'm really excited to talk about my selection function analysis for catalog 2. So it's worth saying that the sample of FRBs that Chime FRB detects is inherently incomplete. And what this means is that essentially every burst that we detect has some probability of detection by our instrument. So for example, there's a burst on the left here, yeah, that's the left, which is very narrow in time and very bright. And this is like the prototypical type of burst that Chime FRB would detect. So the probability of detection is very high. But kind of phenomenologically on the burst in the right is much more wide and scattered. So while it might have a similar affluence, its probability of detection would be lower just because it's harder for our pipeline to detect as it searches. And so the function, I guess, that maps this like universal FRB population, which includes all of these morphologies, to what we actually observe is what we can refer to as the survey's selection function. And we want to kind of put numbers to this concept. Not yet. Okay, so the way that we do this is Chime FRB has this injection pipeline that allows us to directly probe the selection effect in the FRB parameter space by injecting mock FRBs into our real-time search algorithm and determine what their detection status is, so above some SNR threshold that we set. We did this in a large run that took about 10 days in the past March, of about 500,000 injected events, which is nearly an order of magnitude more injections than was done for a similar catalog 1 analysis, except we're approaching it a bit differently. With this, we're modeling the selection function explicitly using a smooth functional form that can assign a 0 to 1 detection probability all across the 4-dimensional parameter space of fluence, scattering time, pulse width, and dn. And for this, we use a logistic regression formalism. So this is a 4-dimensional function bounded between 0 and 1 in the range. So the way we can visualize this is through slices of it. So here is just a 1-dimensional slice of the scattering time detection probability, holding width in dm constant and varying the fluence. So this is increasing the fluence up. We can see that our detection fraction increases. And then we have this kind of decision boundary that approaches to higher scattering times at higher fluences, which is what we'd expect for sources that are easier to detect. And I'll just keep playing this, but I'll also play the one on the right, which is a 2-dimensional slice of this selection function, which is fluence and scattering time varying the width and holding dm constant. And what we can see is this curved decision boundary covariate between fluence and scattering time, which is what you would expect for these two parameters. But what you also see kind of at the beginning of this is this dip in detection probability at moderate to high fluences between 100 and 1,000. And this is kind of a new discovery that we found, that there's a slight dip in Chime FRB's selection at moderate to high fluences, likely due to our RFI masking. So this is great because we can use this selection function across our parameter space to selection correct our catalog 2 distributions, basically by weighting them up, weighting each burst up by their detection probability. And once we have a selection corrected distribution, we can compare this to the actual catalog distribution, and this allows us to improve our intrinsic rate estimate for the sources detected by Chime FRB. And just a note for the community, it is kind of desired in population modeling of FRBs to have some kind of probability of detection by an instrument to do population syntheses and other similar analyses. And this is essentially that. So once this analysis is out, I would encourage the community to use it for refining model FRB populations. So thank you all, and I'll take any questions you have.
have time for one quick question for Kyle.
Hi, I'm Max. I'm a master's student at Amsterdam and an incoming PhD student at McGill. Kyle, on your two-dimensional slice figure where you think you had scattering, yeah.
Yeah.
Why do you reference scattering at 1 gigahertz frequencies?
Well, it was so the question was why we reference our scattering times to 1 gigahertz. This is actually a good point. So usually in the community, it's referenced to 1 gigahertz, although in catalog 1, it was referenced to 600 megahertz, and in catalog 2, it's actually referenced to 400, I think. It might be the other way around, though, but I think it's that. So this is just a way of being consistent across instruments and parameters.
Okay, let's wrap it up there, and let's thank Kyle and all the speakers in the session. We have coffee break until 11:05, but before there's an announcement by Amanda.
Yeah, so okay, so those of you who have been in the transient field for a little bit might have heard stories of buttons at the Great Debate. So for GRBs, there was this great debate of whether they were galactic or extragalactic, and they handed out buttons to mark what we all bet on. So we wanted to do something similar for this conference, and given the topic of the discussion today, we thought it'd be cool to make people pick a side on if all FRBs repeat or if there are repeating and non-repeating FRBs. So though we will find buttons outside, we encourage you to pick a side and spark a lively debate with someone who disagrees with you. And if you cannot choose between the two, we have a third option for the fence sitters that there are N populations of FRBs. And with that, enjoy your coffee.
Welcome back, everyone. Very much glad you're back. I'm Kanti Shah, and I'm going to be sharing this session, which is essentially a continuation of the previous session on populations of FRB. So first up, we have Kriti Sharma, who's going to talk about populations of FRB groups. Take it away, Kriti. Oh no, it's a recording.
Yes. Yeah, so it's a recorded talk, which we will start now. We'll just see if the volume's okay. There's lots of those.
Thank all the organizers for having me here to talk about the past universal characteristics and the corresponding institutions for the partners. Here we begin by a brief overview of the very first FRB. So the first FRB was discovered in Identica in 2021, I was 24. And 1.2 beyond the survey of movement clouds, using the multi-unit river and far to the telescope in Australia. By the main team of astronomers including Chandrayaan, Mark Placing, and Matthew. This first burst, also called the London burst, was detected with less than 500 configurations and about 30 branches left density. Building on the discovery of the London burst in 2007, Continental in 2013 reported 4 FRBs detected using identified to the telescope. All individual configurations occurring at high galactic latitudes, thus providing compelling evidence that FRBs are indeed. Since then, the FRB community has been building a larger sample of FRBs, suggesting that most of them are right about downstream fields activities. They are also believed with less than configurations. About 90% of the population is apparently non-citizens, and most of them are actually extragalactic neobeings. The also rate of FRB is actually quite high, which is 10 by 5 per sky per year. The dispersion rate of the very first FRB development is about 3.5 parts per species, which was far larger than that of the nuclear contribution, which is.
Right, apologies. I think the sound is not being shared online, but it is you are hearing it in person. So we'll just have to fiddle with this for a second. Sorry?
I think there's a thing when you share screen that allows you to also share. There's usually a button when you share screen that is like share audio or something.
Um, is anybody speaking online? We can't hear at all.
Yeah, I'm online and we don't have audio back yet.
I mean, I was asking for Q&A. We can't hear anybody there at conference either. If Vishwangi is speaking.
Oh, it looks like it's hearing us now.
No, it's not.
No, but look at how we're loading up.
We're hearing you now.
Does this work as well?
I think it's through the computer mic.
Testing, testing.
Unfortunately, the input is not the same. We need to fix that. Probably says not. So, I think.
Diggy, do you want to come up and ask your question while we play with it?
Yeah. Sorry for the technical difficulties.
Hey, Kriti. This is Siggy Pleuris from the University of Amsterdam. Nice overview talk. My question was about FRBs that are in globular cluster or satellite galaxy, where the global host properties don't represent the local environment of the FRBs, and if you had any thoughts on how to handle those in the future.
I really think I have a lot of hope with what we can do with timeout triggers and millisecond localizations. I think the best way to go about it is by looking at spatial offset distributions corrected for selection effects. And I think Alexa's going to talk about this later today as well. So she compared the host galaxy normalized offsets for FRBs and separated them out into multiple populations based on their galaxy light profiles. So I think to really distinguish those cases, we should be looking at offsets and pick out FRBs that have relatively larger offsets. And other than that, I think building up a larger sample of nearby FRBs and doing a spatially resolved spectroscopy program would be very helpful, as I mentioned in the talk as well. So we already have it ongoing with several of us. I think Sunil also has an ongoing program for the same. And repeating the same exercise for, say, redshift less than 0.05 FRBs would be very helpful. Yeah, go ahead, Sunil.
Hey, great talk as usual. This is Sunil from Northwestern and U Chicago. I was just wondering if anyone has done like the calculation for checking if radio flares from red dwarfs could be producing FRBs, because all the distributions of the radial distributions of FRBs with respect to their host galaxy seem to be generally just tracing stellar mass and not particularly star formation. So I was just wondering if that channel of FRB progenitor has been looked into.
I don't think so. So, if I recall it correctly from Alex Manning's and Michelle Woodland's work, and then later by Alex as well, I think most of the times the comparisons are done with more of the common transient classes. So, red dwarfs have not really been considered in such comparisons, but I think it's a good question. We should be including that as well going forward.
Okay, testing. Okay, they should be able to hear you. No, it's I think this is also- Okay, yeah. And then are you on PowerPoint? Slides. Slides. Wait, should I just start over? Continue. I just can't find the little share screen. Share. This, yeah, it's up to you, Alexa, but you're totally welcome to use the time to start over. Well, I'll just briefly say for those online, we find FRBs in diverse environments. Either this implies the progenitor is common, that doesn't care where it comes from, or they don't really select for distinct environments. For this project in particular, I was interested in zooming in on the local and thinking about using the locations of the FRBs within their galaxies to understand the underlying progenitor populations. And we'll that smaller. Okay, so the literature gives support for multiple formation channels for FRBs with both prompt and delayed channels. So the prompt channel is largely an FRB that would come from a massive star going core collapse supernova to leave behind a magnetar that at some point gives off an FRB. In this scenario, you would expect to see most FRBs in areas of recent star formation. You don't have a lot of time for the massive star's lifetime for that remnants to travel very far. However, in a more delayed case, such as a compact object merger or accretion-induced collapse of a white dwarf, you would have a weaker correlation with star formation. or even presence on the stellar disk. So for this project, I decided to test the spatial correlation of known FRBs against several different models. So the first one was a smooth stellar light profile. So this is a parametric fit to the galaxies using a Sursic profile. The second one is a model of the residual substructure. So largely this is tracing the spiral arms. So this also comes from GalFit. So the process is you fit these smooth profiles to the galaxies, subtract off that profile, you get the residual. And lastly, motivated by the one FRB we know comes from a globular cluster, I create synthetic distributions of globular clusters. The reason for this is we can only observationally see globular clusters out to a redshift of about 0.1, and the large majority of the sample is beyond that. So instead, I create these synthetic distributions using sort of two formulas for how they are distributed about their galaxies, what I call GC ellipsoidal and GC spherical. In general, these are about 4 times more extended than the observed stellar light distribution. Okay, so those are the models. Next is the sample. So I compile a sample of 37 FRBs, 34 of them detected by the CRAFT team. And these all have optical R-band and infrared K-band imaging. So the majority of the data for this program come from the FRB large program and the Very Large Telescope that we had, about 100 some hours of observing time, which is really awesome. And this is supplemented by observing from several other facilities as well, which I've listed along with the PIs there. Okay, so we have the models, we have the FRBs now to test them. So to do this, my collaborator Adam Deller and I created this model likelihood testing code called CoFlash. Correlating FRB location and substructure of hosts is what that acronym stands for. This is publicly available on GitHub. It's very flexible. If you're interested in using CoFlash, come talk to me. So ultimately, this is a statistical framework to get at the question, which model is the FRB most likely to have been drawn from? So the way this works is you have the 4 models, normalize them to essentially create probability density functions of their spatial distributions, convolve that with the FRB localization, which we assume is a 2D Gaussian, and then measure the model likelihood. So each of the 4 models for every FRB will have a value of the likelihood. The largest one is the most consistent model for that FRB, which I term the preferred model. So what does this look like? So here's a summary bar chart of the 4 models, number of FRBs, which I've split both into the model preferences and the preferences that are statistically significant. So what you can see here is the majority of FRBs do prefer the smooth stellar light profile. It has both the largest number of raw model preferences, but also statistically significant preferences. The residual model, 9 out of the 37 FRBs select the residual, but only a small fraction, 3 out of 37, do so significantly. But it's a little bit more complicated than that, because it turns out that at a redshift of about 0.15 and above, we are insensitive to spiral structure. So for a more apt comparison, when we limit to this redshift range and compare the numbers again, you can see the residual fraction is a lot higher. So this is where the 20 to 46% number comes from of FRBs that are statistically associated to spiral arms. It is interesting to note that when you compare similar redshifts where you see core collapse supernovae in their hosts, about 88% of those occur on spiral arms. We look into a bunch of things in the paper of what could be causing this, and ultimately can't really explain why so many more FRBs are not occurring on spiral arms compared to core collapse supernovae. One thing I should note is that the localization sizes of FRBs are still a lot larger than core collapse, so that could be one of the reasons going on there. I now want to highlight the GC results. So this one that I've highlighted here, the single statistically significant GC ellipsoidal FRB, is the known GCFRB 2021-20E in the outskirts of M81. So this was really reassuring that CoFlash got it right, and it was cool to see that that selection was statistically significant. But if you notice in the spherical bin, there are two FRBs there. So these are 220105A, which is a craft FRB, and 240209A, also known as R155 from Chime. And these have similar statistical significance to the known GCFRB. So this demonstrates that more than one currently known FRB plausibly originates in a globular cluster, showing that not every FRB is associated with the recent star formation, though there is no statistical evidence for every FRB to occur in a globular cluster, just probably more than one. I go into in the paper quite a bit a lot of things that can be driving the model preferences. I don't have time to get into all the considerations, but one I wanted to highlight here is the galactocentric offset, which Kriti also mentioned in her overview talk. So what this is showing is all of the FRBs sort of clumped into two populations. So the disk in this pink color are the FRBs that prefer the profile and residual, and then I've clumped the two GC models into one there. And then I've drawn these concentric circles of effective radius, so that's the characteristic size of the galaxy. So one way you can interpret this plot is sort of a normalized view of where all these FRBs are occurring in their hosts. And so what you can see is that the majority are sitting within this one effective radius boundary, demonstrating that FRBs tend to sit right on top of their galaxies, with only a few found at higher offsets. There is a clear delineation between these two populations beyond about the 2 effective radii contour. Only GC models are preferred, and beyond that at about 4 or so is when they're always statistically significant, though there's just 2, so kind of hard to say if the boundary is actually at 4 or not. So yeah, what I want to take away from this is that the CoFlash framework provides a novel test of globular cluster origins solely from FRB or imaging of the host and the localization. And this is really key for FRBs beyond redshift of 0.1, for which it will be extremely difficult, if not impossible, to ever observationally confirm the globular cluster origin. Okay, so what does this all mean? So this work demonstrates that multiple progenitor channels are required to explain the FRB population. So on the prompt channel side, we find that the majority of FRBs are associated with the stellar disk. It's interesting to note that star formation occurs all throughout galaxies, about 50% on spiral arms, 50% off spiral arms. I thought there would be a lot more going on in the spiral arms than that, but that's what the literature shows. So the takeaway from this is that even though we're only seeing a small fraction of FRBs on arms, they are still consistent with a massive star progenitor, either formed directly on the arms, so these would be the ones preferring the residual, or formed in situ, these would be the profile preferences. However, it's important to note that the infrequency of spiral arm associations can imply that FRBs might not trace areas of high massive star formation efficiency. And when I say massive, I mean like O-type stars. B-type stars are still roughly consistent with their positions. For the delayed side, I find that only a minority of FRBs are consistent with the more extended spatial distribution of globular clusters, with more than one currently known FRB plausibly occurring in a globular cluster, requiring a delayed or dynamical formation channel. We estimate up to 20% could form through these channels. It's a very sort of pessimistic assumption there. I think the true number is a lot lower. But even this high upper limit of 20% is still consistent with global host demographics and magnetar rates in globular clusters. So with that, here is my summary. I want to highlight also, if you are interested in this work, it is on arXiv. There's a lot more there, and I will take questions. Thank you.
Thanks, Alexa, for that talk. So since we are not able to use the catch box, maybe you can repeat the questions from the audience. Okay. Yeah.
Two questions on offsets. So for the, at least for the gallic parameters, we have a sense of what's their vertical offset from the nucleus. So for the FRBs that come from edge-on galaxies, do we have a vertical offset distribution for those FRBs? The second of the question is, for these FRBs that arise from spiral galaxies, do you have an offset distribution for the distance to the closest spiral?
All right, so for online, the two questions were the offset from the stellar disk of the FRBs, and then the second question is the measurement distance from the spiral arm. For that second one, wait a couple minutes for Alex Manning's talk, and that will be exactly answered there. So for the first one, I have, I think, 2 edge-on galaxies in my sample. I don't quantify distance from the disk, but they are largely consistent with being in the plane, so not high up in the halo if this is the galaxy. We don't have this situation, they're more like this.
Thank you.
Yeah.
Yeah, there was a question on yeah, Shami, you could agree.
Shami, if you want to go ahead and unmute.
Yeah, it's not, well, I'll ask it anyway. It seems like your positional uncertainties for the FRB localizations contribute to the models not being particularly sensitive in terms of choices. So presumably in this epoch of milliarc second or 10 milliarc second localizations, they'll get a lot more sensitive. Do you have a sense for how many you would need at, let's say, 10 milliarc second localizations before you'd be very confident in I'm seeing spiral arms or not seeing spiral arms?
Yes, that's a great question, and that is something that I do consider in the paper. So this plot here I didn't have time to get into is essentially what's the like projected size the FRB takes up on the spiral, not the spiral, just on any galaxy. And you're exactly right that even with the selection cuts I've made to have localizations that are smaller than the galaxy size, there's still there's a bit of uncertainty there. So one of the things to highlight from this plot is that the residual panel in particular, you need a localization that is less than half of the galaxy size to tie back to a spiral arm, and even smaller than that for a statistically significant preference. So yes, this is something that, you know, the results are dependent on the localization size. I don't have a number of how many more we would need to better constrain the fraction that are coming from arms, but definitely as many, we should totally keep finding more FRBs and high, good precision localizations that will get at this question.
We unfortunately don't have any more time for questions, but please feel free to reach out to Alexa on Slack or during coffee and lunch breaks. Let's thank Alexa. Okay, so next up we have Alexandra Mannings, who is going to talk about FRB burst properties and local environments. So you'll have 12 minutes to present. Take it away.
Okay, hello. I'm Alexandra Mannings. I just finished my PhD at UC Santa Cruz. Thank you. Today, I want to talk about kind of building a total picture between burst characteristics and the characteristics of the local environments of fast radio bursts. So a lot of the data and measurements that I'm using are from the CRAFT collaboration, with some from other observatories and experiments as well. And of course, largely supported by F4, Fast and Fortunate FRB follow-up, and lots of work from the people listed here. So I guess just starting with the question, are there any notable connections between burst and local environment characteristics, just broadly? But then from there, thinking, well, what might we expect? So starting from a place of some hypotheses or questions. So the first question, for example, could be, do older FRB sources produce intrinsically broader bursts? Or are they associated with highly scattered bursts? So some sort of question about the age or delay time of the progenitor. Another question might be, does the density of stars affect the density of the circumburst media? So does the amount of stars or stellar mass in that local environment affect some other burst properties or characteristics that we see, like dispersion measure, scattering, something like this? And then maybe another question is, on what physical scales might these connections exist? So a lot of our localizations can maybe probe to like parsec scales, but for the most part, we're kind of working on half kiloparsec scales. So if there are some sort of connections to like smaller scale variations or characteristics of the local environment, are we still sensitive to that with the localization precision that we currently have? So, one, I guess, example of this kind of marriage of burst properties and local environment properties that really help to illuminate the possible origins of an FRB is in the case of 2012 1102A, where we saw that it was located within the star-forming region of its galaxy, the star-forming dwarf galaxy, and then also through the measurement of this very, very high rotation measure, as well as some other burst properties, we kind of hone in on this story of an extreme magneto-ionic environment around this FRB, or that this source is embedded within. So these kind of two approaches to answering this question can kind of help us build a more holistic picture of what might be going on. And then we also see this with other high rotation measures as well. There was just an ATEL put out by Kraft for a very high rotation measure burst, and looking at the combination of what the host galaxy or local environment characteristics are with the burst characteristics can help us kind of get to an answer of what's going on. So returning again to our questions of what we might expect, I want to focus first on the first question: do older FRB sources produce intrinsically broader bursts? But really, what I'm trying to say is then, how do we determine this age? How can we use locations of the FRBs within their hosts to understand what their age or delay times might be? So first, I'll just start off by talking about the sample that we use in this study. Some of the requirements were just really bursts with high resolution imaging. So this includes ground-based AO imaging as well as HST. And then all of these have been presented in previous studies, many of which were in the ICS sample presented in Shannon et al. 2024, including some others previously published elsewhere. And we required, well, I guess we didn't require, but we have information on dispersion measure, rotation measure, scattering, fluence, all of these other burst properties and characteristics for most of the FRBs in this sample as well. Okay, so kind of referencing this paper, I think Alexa also referenced this paper. It's very popular with our group. This Aramayan look at the distance of these different types of supernovae, so type 2, type 1 BC supernovae from this shock front in the spiral arms, where we're assuming that at this shock front there is star formation happening from this like compression of the material, creating these dense regions of star formation. And from there, after these sources are born, they drift some amount until this supernova goes off or something like this. So what they do is they measure the distance between from the brightest pixel, or like the peak in the brightness profile of this arm, to the location of the supernova. And they're all normalized by the arm width. So these are normalized distances. Our version is a little more simplified. We didn't do brightness profiles of the arms. We really just say, okay, where is a spiral arm and what is the physical distance in kiloparsecs to this nearest part? It can be an edge, it can be some central part, just whatever location or pixel is closest to the location of our FRB. So we start off with residual images. I'm using 2018-09-16B as an example. And the purple circle or little donut shape is the FRB location. The white is the spiral arms that have been pulled out or highlighted in this residual image where the smooth light has been subtracted away. And then the identified spiral arms are the regions that now have this black hatched kind of texture over it. I did a bad job at choosing what color should be on here, but now the spiral arms are kind of blocked out with this black. And again, showing the FRB location with that purple circle. And the R-min is what we decided to call this. The spiral offset is about 0.008 kiloparsecs between the FRB location and the nearest part of the spiral arm. As I think Kriti mentioned, the distance to the brightest pixel or brightest region in that star forming knot that this FRB is close to is about 250 parsecs. So this makes sense, I think, in the context of that. Okay, so then we also want to compare this or understand what the distribution would be if we're thinking about spiral arms or a disk distribution or a spherical globular cluster distribution, to understand if these FRB spiral offsets show any similarities to the spiral offsets of other kinds of models. So again, going back to our identified spiral arms, so this is our true spiral arm locations in the black. Then we grow that a bit to determine or define some sort of spiral arm model. So that's what's shown in the green. So the green not only includes all of the black pixels and points, it also goes a little bit beyond that, maybe to highlight regions of the spiral arms that we weren't sensitive enough to pick up in the residual images or regions that our initial selection didn't include. So we randomly generate points from this spiral distribution and then calculate our minimum distance to the true spiral distribution. Then we also determine a disk model and a spherical globular cluster model. Again, drawing random points using the smooth light distributions that were, or specifically for the disk model, using the smooth light distribution that was determined by Galfit, and using this to then create a PDF from which we can draw random points. And again, measuring the minimum distance between these random points and our spiral arms. And then the same for a spherical globular cluster model. And usually, or in many cases, the globular cluster model does extend beyond what we see here in the disk, but for 1809-16B, it's a bit more concentrated towards the center. Okay, so this is what we find. We show the FRB distribution, a CDF in black, and then we're also comparing against some measurements, similar measurements that we found in a paper from the 90s, 1994, which did a very similar thing that we did, just looking at the physical distance between the location of type 2 and type 1a supernovae to the nearest spiral arm. So we show that in this kind of pink and orange colors, and then showing our smooth distributions from the models. And in general, or in this current iteration, we're able to reject the null hypothesis that FRBs are drawn from the same distributions as the spiral, the random, so just random points across the image, and disk distributions and models, but we don't or are unable to reject it for the supernovae of either type, type 1a or type 2, or the spherical globular cluster distributions. Okay, great. So then using this now age kind of measurement, looking at this distance from the spiral arm, we asked the question, does this distance correlate with burst intrinsic width? So we're looking at the width that encompasses 95% of the fluence of the burst and our min or spiral offset, and we don't find any notable or strong correlation between the two at this point. Okay, and ending with our second question, does the density of stars affect the density of circumburst media? Or in other words, like, are there environmental effects on these burst properties? And so we take a look at the stellar mass surface density. So that's in terms of stellar mass per kiloparsec squared against the 1 gigahertz scattering time, and also again that burst width. And we find a moderate but statistically insignificant correlation between the scattering time and stellar mass surface density, and then we find no notable correlation between stellar mass surface density and the burst width. We also look at fluence against these different measurements, the stellar mass surface density and minimum offset from spiral arms, and don't find anything there either. So no strong correlations. Okay, and my summary. So there is this possibility of using this minimum spiral offset as a way to understand FRB progenitor or source drifts and ages. And then in our exploration of looking for correlations between burst properties and local environment properties, we do not find any strong correlations, but we should keep looking. Thank you.
Thanks, Alexandra. Questions? Oh, yes, Stella.
Really nice talk. I was wondering, also planning to look at correlations between burst properties and, say, star formation rate, and also post-DF.
So we did look at burst properties, and then we looked at scattering and star formation rate, and didn't find anything. Looked at star formation rate like globally, presently or current star formation rate, as well as in the past like 100 mega years or something, and didn't find anything there either. Yeah. Oh, and hostium. Yes, we did do that. And didn't see anything. Sorry. But that doesn't mean it's not there. Just that, yeah, it wasn't present here.
Okay, are there any online questions? Okay, so let's thanks Alexandra again. For our next talk, we'll have Hugh Roxburgh, who is going to discuss if most FRB hosts are disturbed, which is going to be on Zoom.
Hello, can everyone hear me? I can just share my screen if that's possible, or if that's not possible.
Yeah, it should be. I'll just stop sharing.
Cool. Apparently I've had to request to be able to share my screen.
Yep, should be good now.
Sweet, cheers, thank you. Cool, can everyone see my screen?
Yeah, I'll just full screen it. I've done this so many times.
I misguided you.
There's not the top. I see. Yeah, should be good.
Yeah, go ahead.
Go for it.
Cool, cheers. Okay, hey everybody. My name is Hugh, and I'm a second-year PhD student here at Curtin University in Perth, Australia. So I currently have a perfect 12-hour offset to time, which is amazing. Now, just now, we've kind of heard a lot more in your morning about the optical properties of the host galaxies of FRBs. But today I'm going to delve back to radio wavelengths and cover the distribution of H1 emission in these galaxies in order to answer this question: are most FRB host galaxies disturbed? Now, for those who aren't super familiar with H1, this is the signal that is emitted by atomic hydrogen gas, essentially large groups of neutral hydrogen atoms that are all clumped together. This emission arises due to quantum mechanics, where the single-bound electron orbiting the hydrogen nucleus prefers to exist in one spin state over the other. And as a result, there's this energy difference between the level of these two states, and so this atomic hydrogen can be excited when it absorbs some energy and then spontaneously relaxes back down to its ground state and re-emits that energy as radio light with a wavelength of 21 centimeters. Now, H1 is an incredibly useful tool for host galaxy, or just for galaxy studies in general. It is generally the most abundant gas in galaxies, and as you can see here, it often extends far beyond the optical disk. And so, as a result, H1 emission encodes a whole bunch of information about the large-scale kinematics of galaxies, and is far more sensitive to perturbative dynamics that may be subtly affecting their evolution. So this can include any internal outflow mechanisms, such as those that are driven by AGN, or any external tidal disturbances from gravitational interactions with nearby galaxies or gas clouds. Now, as has kind of been covered already today, FRB hosts generally are star-forming galaxies for the most part, and so we do expect that this is a good thing because we expect to see H1 emission coming from star-forming galaxies, because atomic hydrogen gas is the fundamental fuel for star formation. So if you have these high star formation rates, you need a lot of fuel, and therefore you are likely to have a large gas reservoir that's able to emit in H1 as well. And as a result, we are able to probe the underlying dynamics of FRB host galaxies using this alternative regime as well. Now, prior to my work, only 5 FRB host galaxies had been observed in H1, but there was an interesting trend that emerged. All 5 of those host galaxies exhibit a highly disturbed H1 profile, all of which have been attributed to recent merger activity. So, for example, here is the H1 spectrum of the host galaxy of FRB 2018-1030A, which shows this characteristic kind of double horn shape that we expect, but also has a significant asymmetry either side of the middle. And this is a hallmark sign of disturbance in these types of profiles. Now, here's another example where we have a contour plot that shows the spatial distribution of H1 emission. And for those unfamiliar, we call these intensity maps. And the more central your contours are, the stronger the emission. What we can see here is that there is a tidal tail feature, as we call it, which is a bunch of gas mass that has been stripped or ejected from the main gas clouds surrounding the galaxy. And in this paper, it was concluded that this is most likely caused by gravitational interaction between the host at the top and this kind of sliver of a satellite mass below. Now, this 5-to-0 disturbed to undisturbed ratio is an interesting observation. Merger activity has been shown to potentially stimulate or amplify star formation. And so if we're seeing that most or even all of our FRB hosts are disturbed in this way, that provides further evidence that might support these fast channel progenitor theories associated with star formation. Of course, I've talked about 5 examples, so we're definitely in the regime of low number statistics, and we want to expand that sample as much as possible and increase the number of FRB host galaxies observed in H1. And that brings me to my work, which aims to do just that in order to shed more light on this kind of emerging trend of disturbance, and also to simply look for any interesting characteristics in the H1 derived properties of FRB host galaxies. So where do we start? Well, we need a sample. And for us, we determine the FRBs to be included in the study based on 2 criteria. Firstly, we require that the FRBs have robust host associations, which we define as having path probabilities greater than 0.9. Secondly, we require that the host redshift is no greater than 0.1. And this is due to the fact that the H1 signal is inherently pretty faint. And so the upper redshift limit for secure detection is currently around 0.1 with current generation telescopes. Thus, we are left with this sample here of 14 new targets, which nearly quadruples the previous sample size. Now, the group in the first section here are targets that we put in dedicated observation proposals for last year with the GMRT in India, FAST in China, and Meerkat in South Africa. And those final three at the bottom are CHIME targets, which were reported earlier in the year. And so that was well after proposal deadlines, but they had archival data sets that were available that we could just access online. So what do we find? Well, here are all the spectra from these targets. And you'll see that 13 out of 14 of them are indeed emitting in H1. The single non-detection that we have happens to be the one galaxy in this study that, according to previous optical studies, is transitioning towards quiescence. So it makes sense that it has a much smaller gas reservoir, and this is not exhibiting a strong H1 signal. Now, for the rest of them, how do we determine whether or not they're disturbed? Well, we can do this in two ways. So firstly, we can use our eyes. Does the spectrum look funny? Does the intensity map show significant deviations from a smooth disk? This is pretty self-explanatory, but is also quite important, as I'll get to in a moment. However, we also want to be able to quantitatively compare with the background population of random local universe galaxies, and so we also do utilize common metrics to describe the level of disturbance in these profiles. Now, due to time constraints, I won't really go over the metrics in detail, and I won't talk about the thresholds above which we consider a profile to be disturbed. All you need to know is that there are a lot of them that we use, and they're all kind of tied to the asymmetry of emission about some central rotation axis. So for example, in one dimensions, you can set the center to be this certain channel, and then you measure either half of it, for example. In two dimensions, you can compare each pixel and then rotate the whole intensity map by 180 degrees and do some comparison. And then you can also extend this into three dimensions by taking a centroid in space and also a central channel and rotating every voxel around in our data cubes. So what do we find? Overall, of the 13 detections that we have in H1, we find that 6 of them are indeed disturbed. We can see in the top left, there's a pretty strong tidal tail, as I showed earlier. And in the bottom middle one, we have an FRB host that's going through a major merger with a much, much larger galaxy. And so their H1 clouds are kind of overlapping. Now, the bottom two corners are two of the archival data sets. So we don't have spatial H1 information, but their spectra qualify them to be considered disturbed based on our metrics. And if you look at optical survey imaging, they potentially allude to some level of disturbance, but obviously that's very speculatory. We have to get some more H1 information to fully figure this out. Now, you might be wondering how we consider the top right one to be disturbed. And this is one of those cases where the metrics just simply aren't enough, and you kind of need to use your eyes to be able to figure this out. When you look at just the spectrum and just the intensity map, and you take them at face value, they appear mostly as we expect for a rotating disk. However, this kind of slight bumpiness along the northern edge actually turns out to be a pretty significant gaseous extension along the northern side, which was only revealed when we went deeper with this individual channel map inspection. And this is likely caused by some nearby dwarf galaxy churning up the gas along the side. But as we don't have redshift information for all the potential neighbors, we can't rule anything out for certain. Now, importantly, we do find that 4 of our targets are undisturbed, with symmetric spectra and spatial profiles that follow a smooth rotating disk. Sorry, and just to reiterate, such examples have not been demonstrated so far in FRB hosts, so it's kind of important to be able to see that these things definitely can be settled. We also do have 3 other targets which are either too low signal to noise or too low resolution to be sure about, and so we exclude them from the rest of our analysis. Now, where does that leave the question? Are most FRB hosts disturbed? Well, as with a lot of science, it's complicated. Prior to this work, we had the pretty unambiguous ratio of 5 to 0, but now the ratio of ones that we're confident about is 11 to 4. And so the question that I'm sure many of you are wondering, what ratio do we expect what ratio do we expect the trend to follow if the trend isn't real, if that makes sense? And this isn't very easy to answer. Many previous studies have used the metrics that I briefly talked about to measure disturbance in different samples, with some looking at isolated galaxies and some at galaxies in groups, and a bunch of them choosing a whole bunch of different...
You have 2 more minutes, Hugh. Sorry to disturb.
No, you're good. Thank you. Awesome. And many of them are choosing completely different thresholds above which the profile is considered asymmetric. So based on those quantifications, those studies have found anywhere between 10 and 40% of galaxies show disturbance. However, because we've investigated our sample into a lot more depth by looking at those individual channel maps and being a bit more precise, we kind of have to do something a bit different. And so based on that literature rabbit hole, you're just going to kind of have to trust me on that. And to account for the extra depth that we've gone into for these targets, we roughly estimate that a one-to-one disturbed to settled ratio is a conservative estimate for the expected ratio of FRB hosts. So if we expect a ratio of 1-to-1 and we observe a ratio of 11-to-4, then we clearly still have an excess of disturbance going on here. If we assume Poisson error and perform a significance test to reject the null hypothesis that the FRB hosts should follow this 1-to-1 ratio, we find a p-value of 0.065. So this is not quite at the level of significance that we tend to require, but it's really, really close. And unfortunately, what that means is that we need more data to be able to actually fully rule anything out. That's also science. We love it. Now, briefly at the end of this talk, I'll just highlight a few of the H1 properties of FRB hosts and point out anything interesting. So this plot here looks at H1 mass on the x-axis and star formation rate on the y-axis, and our FRB hosts are overlaid in red and blue on the X-gas sample. Now, on the whole, we can see that FRB hosts are generally pretty massive in H1 because they're on the right side of this plot. And this is very much in line with what we've heard in the past in terms of having somewhat like larger stellar masses and a deficit of lower stellar masses. Now, I've also separated these hosts into red for non-repeating hosts and blue for repeating FRB hosts, apparent non-repeating hosts. And by eye, and also if I put some circles around some things, you can potentially see a distinction between the masses where repeating hosts are falling to slightly lower masses. Now, you won't be surprised that this distinction is not very significant. It's not a statistically significant thing, but it is at least the fourth case in the literature where we were seeing a potential preference towards slightly lower mass galaxies for the hosts of repeaters. And I should note that none of our repeaters hosts are included in those previous samples either. So this is definitely something to keep an eye out on, but so far not statistically significant. Now, I'm probably running out of time. This is kind of a plot that I was going to show that basically just suggests that beyond what I've just shown, the H1 properties of FRB hosts are very varied. We span a whole range in this domain and a bunch of other comparisons that I could make. So much like the optical FRB hosts in H1 are also widely varied. And yeah, I'll just leave you with my summary slide. And the paper is going to be submitted tomorrow is the plan, maybe Thursday. We'll see. But yeah, thank you very much. Appreciate it.
Thanks, Hugh. Do we have any questions? Adam.
Thanks for the talk. I guess you'll like the question. You done any follow up to see if any of these hosts are identified in galaxy groups or other environments? We're starting to see a lot. Some other FRB hosts that are in these multiple galaxy systems.
So Hugh, this is a question by Adam Landman, who's a postdoc at MIT. The question is whether you have done any follow-up to see if these disturbed hosts are in galaxy groups, because we are finding more and more FRBs which tend to occur in galaxy groups.
Yeah, great question. So we because of these, particularly for the observations that we have with GMRT and Meerkat, we can look much wider in the field at to see if they're in H1 rich groups, and we find that a lot of them are in groups that are in regions where they're within 2-3 megaparsecs of other H1 detections as well. So we didn't see a significant there was some disturbed galaxies that are isolated apparently in both optical and H1 detections, but there are some that are very nearby, and there are also some of the settled galaxies that we've also seen, which are in really close to other galaxies, but they appear to be settled. So there wasn't a huge trend, but we did observe that cutoff. Yeah.
Okay, we probably go to online question.
Yes,
Oh, Sunil, can you unmute and ask your question?
Oh, yes. Great talk, Hugh. I was just wondering if you had the resources and the time, what kind of galaxies would you choose to build your field population with to do this comparison? in the future.
So do you mean as in like if you to compare with random galaxies in the not necessarily
Yeah.
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 So I guess the idea is that we kind of want to build our comparison population with things that are similar in mass and star formation rate. So we tend to want to look at things that are that are massive and probably massive spirals that have gas in them. A lot of those previous works, for example, if I just skip back to this slide here, where you can see like LVHIS and halo gas, those were populations which were notably in isolated fields. And so it's kind of tricky with so many different ways of quantifying this asymmetry and this disturbance to pick out certain populations to compare with. But we'd really like ones that are kind of representative of local spirals, if that makes sense. Kind of more along the lines of these gray dots in the X gas sample, which are likely to be more gaseous because they are detected in H1, if that makes sense.
Thank you.
Okay, we don't have time for more questions, but please feel free to ask your questions.
Yes, ask on the Slack,
So
please.
let's
Cheers,
thank
thank
you
you.
again. And next up, we have a lightning talk by Ben Stapers about hunting FRBs with Mirror Trap. And just a quick reminder again for people asking questions to introduce yourself first. And you can take it away, Ben.
Right. Hello. Thanks, everybody, for attending and giving me the chance to give a talk today. Sorry, just trying to find a way to so that you can actually start to see me. Yes, thanks very much for making this possible and for allowing me to give a talk to quickly summarize 5 years of Mirror Trap. You heard a little bit about this already from Kaustub yesterday. So it's a project that runs on the Meerkat telescope. It does fully commensal observing. We also have this opportunity to do simultaneous optical observations with Meerlicht as well. And we've been running approximately 5 years now. This is clock time, not wall time. So it's probably closer to 2 to 2.5 years of on-sky time. Of course, these things aren't possible without a large group of collaborators who have supported us over the years, and we're very grateful for all of the work that these people have put in the past and hopefully in the future as well. Also, thanks to Soreo for their support of our observing campaigns, and also to the Meerkat observers who have been graciously allowing us to be commensal with their observations, and also to the Max Planck Institute for Radio Astronomy for providing some of the hardware that we use. So wanted to just give you a summary of where we're at after this amount of time. So we have a sample of 78 FRBs approximately that we found so far. And what you can see here in these graphs is the fact that we actually do 2 experiments in one, in a sense. So we have the capability of observing in the coherent beams, which have a sensitivity which is somewhat higher than those in the incoherent beams. And so these plots are showing you the FRBs that we found and the distribution as a function of DM. The top left-hand plot is showing all the sample, which has a median DM of around about 870. And then the lower 2 plots are the ones that probably of most interest. Those on the left are the ones that are detected only in our most sensitive beams, that is the coherent beams, and the median DM of those is around 730. And then in the incoherent beam, we have, which is, like I say, about a factor of a few less sensitive, a median DM, which is actually somewhat higher. And by comparison, the median DMs are around 400 to 500 from a lot of the other experiments. Of these, we have around about 31 voltage dump triggers so far, around about 35 localizations, and so far around 14 of those we have redshifts for. We also observe in multiple frequencies, so about 53 FRBs have been detected in the L band, 24 in the UHF, and still only 1 in the S band so far. And you can see that they have a range of different dispersion measures. We have a nice paper that should be out this week in the archive, led by Ines, which has got 15 of our currently one-off FRBs, 11 localizations, 9 host galaxies, and 6 with redshifts. And so we're with lots of different hosts, which will add to some of the nice talks that we've just been hearing about. We have 2 repeaters so far. You'll hear about one of those in a talk by Kavya a little bit later on today. And the other one is at a DM of around about 830, but a very, very low RM. And we're currently following that up with telescopes at the moment. Given the time, I'll just also note that there'll be a nice talk by Jun Tian later this week, talking about the fact that we found also more than 100 new galactic sources. And so in summary, we found around about more than 75 new FRBs. We probed the high-end region of the DM space. We can localize them using the transient buffer to get the hosts and the redshifts. These high redshift hosts that we hope will be associated with some of these high DM FRBs will tell us something about the origins. And they also pave the way for cosmology. We have around about 2 repeaters, which seems to fit with the statistics so far. We have some nice fields where we've been able to go very, very deep. And so we have a population of FRBs in these fields, which will be interesting to follow up. And I'll stop there. Thank you.
Thanks, Ben. Okay, so Vicky, questions.
Is it surprising that the median are lower in the beams for which there's greater?
Okay, Ben, this is a question by Vicky, and the question is it surprising that the median DMs are lower in the beams which have greater sensitivity?
Yeah, it is interesting. We're pondering that ourselves. We're not quite sure we understand that yet, and whether it's a significant difference is the first thing that we need to check on that.
Okay. Is there any online question, Kyle? Is there any online question? No. Okay, so let's move on to our. Okay. They can just unmute. Emmanuel, can you unmute, please?
Yeah, sorry, I'm so sorry. Quick question for you, Ben. Many thanks for the nice talk. It will Meertrap, from my understanding, there will be additional dishes added to Meerkat. Will Meertrap run in that era?
That's currently under discussion. That's currently under discussion, I guess, is the best way to say that.
Cool, great. Hope so. Thank you.
Okay, let's thank Ben again. And next up, we have Michelle Woodland, who is going to talk about highly dispersed FRBs. You'll have 3 minutes.
Yep. I think we need to share this again. Was yeah. What? Oh, yours.
Hi, everyone. My name is Michelle Woodland. I just finished up the first year of my PhD at UC Santa Cruz, working with Brian Gainsler. A few people so far have mentioned the AO host work that I've done previously. I'll be talking about none of that. Instead, I'm talking about how the work I'm doing with CHIME now, which is exploring the nature of highly dispersed FRBs. So why we care about high DM FRBs in particular is that they're either high redshift, have complex environments, or intervening material, or both, either of which would be really neat. And so in particular, I've been looking at the high DM FRBs in CHIME Catalog 2, of which there are 42 of them that have extragalactic DMs over 2,000 parsecs per centimeter cubed, so pretty high, the distribution of which can be seen on the plot on the right there. And so typically, They're lower signal to noise than their lower DM burst counterparts. However, analysis can still be done to reveal their origins. And there's just a handful of example waterfall plots at the bottom here. And so there's a lot of different possible explanations for why a burst might have a high DM. For one of which, maybe the most obvious is that it's a high redshift. For example, for reference, a burst with a DM contribution of about 3,000 would say be at a redshift of 3-ish. There could be an intervening galaxy cluster, which is already shown to be possible for a handful of FRBs in Liam Connor's work. H2 regions within the FRB host galaxy can contribute a non-negligible amount to the host DM. As well as just complicated dynamics within the nucleus of the FRB host galaxy. For example, within our Milky Way galaxy, our galactic center magnetar has a DM of almost or over 1,700 just within our own galaxy. So that could contribute non-negligible amounts to the DM as well. As well as there could just be an intervening galaxy or galaxy halo or perhaps multiple that could also contribute to the DM of the FRB. So now we have all these possible explanations, but how do we actually go about determining the source of high DM? There's a few different things that we can do. For one, we can simulate DM contributions from different sources, for example, which I've already done with galaxy clusters, which can contribute significant amounts on the order of, say, like 2,000 DM units to the FRB DM. We can compare the low DM and high DM populations from CHIME Catalog 2, in particular, looking at statistical differences between some properties. For example, scattering timescale, which I'm shown here on the right, scattering timescale versus DM. And it seems like perhaps for our higher DM bursts, there's as well, they have higher scattering timescales, which makes sense if they're going through more material, they have more opportunities to be scattered, but there's still a very wide distribution within that. And so we can also look at imaging surveys for objects in the FRB line of sight. For example, can we see a galaxy cluster in a survey like decals? That would be a really obvious red herring. And we can also examine the corresponding baseband data for these bursts. For example, the one red dot I have in the plot here, it's a burst FRB2020-0124D. We do indeed have baseband data for it with CHIME. It has a DM of about 2,700 and a scattering on the order of 60 milliseconds at 400 megahertz. And so now we're going through the process of running all of the CHIME baseband reduction pipelines and haven't found anything of super important so far. But with the CHIME intensity data, we're talking localizations on the order of 10 arc minutes. With baseband, it's on the order of an arc minute. But we're also really excited to see what we can do with CHIME outriggers when we're talking on localizations on the order of arc seconds. So we can really definitively define a host association to see why these bursts might have high DMs. Thanks.
Thanks, Michelle. Questions? Online question? Okay, so I can ask a question. So in the population synthesis work done by Caitlin Chen for CHIME FRB Catalog 1, we saw that we predict that most FRBs detected by CHIME would be from less than redshift of 2. So what is, do you have a sense of how many of these FRBs with DM greater than 2,000 would actually be at high redshift?
Yeah, so that's obviously a question that we're trying to answer, at least in terms of looking at say if galaxy clusters would be a really obvious option. It seems like maybe only 2 out of the 42 seems like there might be an intervening galaxy cluster. So then maybe most obvious after that is high redshift. For at least this one burst with baseband, we recreated the analysis of Cords et al, where you can use the DM in combination with the scattering to set an upper limit on the redshift, which would be on the order of 2.6 for this burst. So potentially some really high redshifts, but yeah, something we're still looking through.
Okay, great. Okay, let's thank Michelle again. Okay, we'll just give a couple minutes for
No, it's good.
Oh, are we not fixing the tempo?
No, for the other slides, everything works. It's just
okay. So next up we have Daniel Kelly, who is going to talk about the sub-second periodicity FRB. You have 3 minutes to present.
Okay, hello everybody. Hope you can hear me all right. So this is a talk that nobody would like to ever present, but here I am, and here we go. My name is Daniele Michilli, and a few years ago I discovered this source, this periodicity in a source detected by chime FRB. So basically, I found out that the separation between the multiple components of this burst arrived with a clear periodicity. And at the time, we spent a lot of effort convincing ourselves and the referees that this periodicity was real. And it suggested a neutron star origin of this FRB. Now, the zero hypothesis in the paper was that this could have been a galactic source, but we excluded the case because we didn't find in the direction of the source any evidence for a counterpart that could explain the high DM and scattering excess. Now, recently, a new subsystem of chime called Chime's Law came online, and Jeff will tell us all about this later in the conference. And this new system started finding a galactic pulsar that showed striking similarities to the previous source that we published. In particular, all the parameters that we derived from these 3 seconds of data are compatible with the galactic pulsar, except for the declination, which is 20 degrees off. So at this point, we're pretty certain that this periodic fast radio burst, we rediscovered a periodic pulsar, and this is just a galactic source instead. So the question we need to answer is why the declination was 20 degrees off and we didn't realize it. First, let me tell you that we found out about this just last week, but we wanted to inform all the community as soon as possible. And the analysis I'm presenting are still developing. We believe what happened is a heavy rain when we observed our daily calibrator, together with a particularly strong RFI and some probably malfunctioning of our software. All these rare occurrences together brought part of the band of the telescope to be pointed to look at the wrong direction of the sky. We daily check pulsars that are in our beam, and we didn't notice anything unusual on that day. And we believe this is because the problem was only in a small fraction of the top of the band, but this pulsar is highly scattered, and so is actually much brighter in the top of the band, contrary to most of the other pulsars. Again, we believe that this is a very rare occurrence, but we are currently investigating the problem, and before we panic about every single detection that we published in the past and that we are currently preparing, we are confident that the vast majority of our localizations are correct, but we are currently working to triple check that all our localizations are right. including those that will be presented in Catalog 2. So what happens now? We are in contact with the nature editors, and we are discussing with them the next steps, and we'll submit a note as soon as our analysis of what happened exactly is completed. And as we've done that, we'll also put additional checks in place to prevent this from happening in the future. Before a week ago, we didn't even know that this failure mode was possible and that our system could be 20 degrees off if this rare combination of events would have happened. So on behalf of the collaboration, I want to sincerely apologize to anybody that put effort studying this source. And again, we are working hard to prevent this from happening in the future and to triple check that all our localizations are correct. Thank you.
Thanks, Daniele. Do we have any questions?
There were two other slightly lower sources who were in the second generation quality here. You have there. Are they still getting or do we have to take that?
Yeah, thanks for the question.
Sorry, can you repeat the
Yes,
question?
I'm having to get from Frankfurt. Yeah, I asked this question.
Can you repeat the question?
Yeah, absolutely. Sorry about that. Yeah, so the question was that in the paper we published, there were two additional sources that presented some form of quasi-periodicities, although not with the same significance. And the question was that if those sources are genuine or galactic as well. From all our preliminary checks, these sources seem to be genuine. They were detected on completely different days with different gain solutions. So we are confident that they are genuine.
So you and your team, this is Yuri van Leeuwen from Astra, you and your team have made many amazing discoveries. And so, of course, it's possible that sometimes a mistake gets made. And our field moves forward by many genuine discoveries, but it moves forward especially if people are transparent about what happens. So I really want to commend you and the team for standing up and sharing with us this result. And I think it's a big.
And I want to thank you for the very nice response. I wasn't sure I was going to get it. And it's another demonstration of how wonderful this community really is.
Okay, so thanks, Daniele, and we can also head off.
Thank you.